You can run a ram air turbine. You can have an electric pump to operate the hydraulic system in the event of emergency, and you've also got the air turbine. Yeah, you could use an air turbine to run the pump. So without seeing the question, I haven't got the questions in front of me, but if it's talking about normal and emergency, you can have an auto setting or a normal setting for your pump, an on-off switch, and then you've got the alternative systems that you could use.
Okay. All right.
Okay.
Okay.
Right. Well, we're on a roll. Has anybody else got any questions from yesterday? And for those I haven't said good morning to, good morning, namaste.
Namaste, Jim.
Good morning.
Right, so if no one's got any questions, we've got a fair bit to get through this morning. Well, I say a fair bit. There's a few bits we need to wrap off. We'll get flying controls out the way this morning, and then we'll do the first part of landing gear this afternoon. So that the next section that we need to look at is fly-by-wire. Yeah. A lot of more modern aircraft now are coming into the fly-by-wire umbrella, although older aircraft technically do have some fly-by-wire systems on them. But when we talk about fly-by-wire, we're talking about the larger aircraft, and we're talking about computers doing all the work for us. Yeah, the computers thinking, anticipating, sending signals to the hydraulic actuators, and expecting an immediate response from those actuators. So the fly-by-wire system, very fast, very responsive. Few other advantages it has. Can everybody see the presentation okay?
Yes.
Yeah. Right. Yeah. Got to make sure in this day of technology. Yeah, so large aircraft, yeah, we're going to make for a nice smooth flight. The aircraft's going to be responsive, and we can manage the weight distribution, the fuel distribution, to make it more fuel efficient. So some of the advantages of our fly-by-wire then, weight saving, yeah, because we haven't got all the conventional components in there. We're just using electrical wires and computers, and nowadays they're very lightweight, so there's a good weight saving advantage. Nowhere near as much maintenance required. Take a black box out, put a black box in, pod your button, and the systems will run through a self-test. So the downtime is reduced greatly. Gust load alleviation is where we can use the ailerons and the spoilers to offset the effects of any wind gusts. Yeah. So if the wind gusts upwards, the stress on the wing, by flicking the ailerons and the spoilers to oppose that flexing, we can reduce the stresses on the wing and make the ride more comfortable for the passengers. What else are we going to do? The maneuver protection, yeah, it's quite possible for a pilot to maneuver the aircraft outside of its limits. It could overstress the aircraft, overmaneuver the aircraft. But with a fly-by-wire in a large aircraft, when the pilot moves the controls, the computers will sort of amend the inputs from the pilots to give him the output that he wants, but without the rapid moving of the aircraft to overstress it. So the manoeuvre envelope is going to ensure that the pitch and the yaw and the angle of attack and the G-forces, all the rest of it, are not exceeded. Yeah. Much better handling. The aircraft becomes far more responsive to pilot inputs. It'll automatically. It says in a bank. Yeah, if we're doing a turn, rather than the pilot having to hold the nose up at the same time as rolling the aircraft will do that for him. It'll automatically compensate for the onset of Dutch roll. It'll look at the amount of rudder that we need in a turn, all the rest of it. So the fly-by-wire is actually looking at the manoeuvre that's being requested, anticipating what's going on, and moving the controls accordingly to give it a nice smooth effect. Yeah. We're going to save on fuel. One of the reasons for that is the aircraft can manage the fuel contents, and by keeping the fuel systems within 2% of the mean aerodynamic chord, that alleviates the drag on the aeroplane, and means that we don't need to provide as much thrust, obviously, and reduce drag. Looking at the amount of download on the tailplane that we've got to have, again, that's going to reduce your drag. So significant fuel savings on fly-by-wire aircraft, which is what companies want. Yeah, save money. So the fly-by-wire control system, is a series of computers looking at the pilot's inputs, anticipating what the pilot wants to move, and reacting rapidly to those demands. Yeah. Fly-by-wire system, page 147, just under the concept of fly-by-wire. To provide improved handling, allow the aircraft to fly with more relaxed stability, the computer must be made to do more. So that the computers are actually, they're not just passing information, they're actually thinking and saying, right, this is what's needed, this is what's needed, this is what we're going to do. Yeah, and for that reason, the fly-by-wire system's often referred to as an active control system. Stick a highlighter through that, please. Yeah, the fly-by-wire system, often called an active control system, because the system itself is doing more than just passing instructions on. Yeah, it's analysing, as I say, anticipating, analysing, and amending the signals that are being sent out. To that end, the active control system's got to use fast-acting computers. And the actuators have got to be really, really responsive, to make sure that the demand is immediately fulfilled. There's no delay in operation, and the feedback from the actuators to the computers, so the computer knows exactly what's going on every microsecond. Again, page 147, the paragraph third from the bottom there, the general layout of the components in an active control system. That's the computers, what the computers are doing, how they're comparing each other. So all the components and what they're doing. The layout of those components is known as the architecture. Yeah, highlight. And the manner in which the computers create control surface movements and their aircraft movement is known as the control laws. Yeah, we'll come back to the control laws in a few minutes, but all the equipment generally all laid out. Yeah, all the gubbins, the actuators, the inputs, all the rest of it is the architecture, and the response to that input works under the control laws. Ta-da. Yeah, within that as well, obviously, we're going to have backup, as we'll see in a minute. So every system has got plenty of backup, so if anything does go wrong, we've got lots and lots of fallback. Again, the control surfaces, and we've seen these till we're blue in the face, where we've got the ailerons, we've got the spoilers, we've got the elevators, we've got the rudder, we've got the trimmable horizontal stabilizer or the variable incidence stabilizer. And the notes go through a couple of example systems. I'm duty bound to go through them, and as I do, I'll just keep an eye on the text just to make sure that anything that's there does get highlighted. So what we're doing with the fly-by-wire system, yeah, we're going to use it to operate the control surfaces. So the control surfaces are monitored by a series of computers. Yeah, and those computers are going to send signals out to the control surfaces that they are responsible for. Yeah, two types of control computer. In the example we've got the elevator aileron computers, the ELACs, and the spoiler elevator computers, the SCCs. Primary functions of the computers are to control the aileron, elevator, and trimmable horizontal stabilizer, and provide spoiler control and alternate control of the elevators and their horizontal stabilizer. Yeah, they're considered the primary control. Two computers of the ELAC type installed. Each of those achieves control and monitoring of one actuator in each aileron and elevator. As we'll see in a minute, because we go through each of the systems in turn, but the actuators in the system are going to be duplicated. We're going to run multiple hydraulic systems, as it says here, 3 independent hydraulic systems, and also we've got the mechanical pitch trim as a fallback on the fallback. Yeah. So your ELACs monitor 3 electric motors which control the trimmable horizontal stabilizer. The SCCs provide control and monitoring of the spoiler actuators, and in addition, the SCCs give you alternate control for the elevators and the horizontal stabilizer as well. Yeah, the example system, it's just showing that we've got 3 hydraulic systems. We don't need to worry about that. Bottom of page 148, definitely worth knowing that the computers are supplied from the DC essential bus bars and the DC normal bus bar. Yeah, the bit at the bottom of page 148 that's worth highlighting is the fact that digital systems only use DC, so they can operate from the aircraft batteries if required. Yeah, so main supplies taken from the DC essential bus bar, normal bus bar for the other computers, and if we lose bus bar voltage, the battery will supply. But the bottom line, please stick your highlighter through that. Digital systems only use DC. So what we're looking at here, yeah, the side stick controller. Now, depending on whether we've got a Boeing or an Airbus, depends on the method of input. I think it's Airbus that use the side sticks, and Boeing tend to use a conventional stick, even though it's a fly-by-wire setup. The side stick commands go to both sets of computers, the primary system, the normal system, the ELACs, and the ELACs sending the signal through to the actuators on the elevator. Yeah. Also from the ELACs, signals to the motors for the trimmable stabilizer. Yeah. Should we get a failure in one of the ELACs for whatever reason, then the SECs will take over. The SECs will kick in. You get the alternate control, and from the other SECs, again, it clicks over the alternate control, and we can still run the stabilizer and the elevators. Multiple hydraulic motors, multiple actuators running off different systems. So again, we're going to maintain control. What normally happens is one of those actuators will be active and the other one will be damping. But as soon as anything happens, the actuator that's in damping mode will take over immediately. Yeah, so pitch control provided by the horizontal stabilizer, 2 elevators controlled manually from the side stick controllers, each operated by hydraulic actuators, 1 actuator in active mode while the other's in damping. Should an actuator fail, the functions reverse. Yeah. In event of total loss of electric power, the actuators automatically go to centering mode and will hold the control surface in the neutral position. And position feedback and monitoring done by transducers. We'll have a look at those in a minute as well. Yeah, if we get a total failure of the hydraulics and the electrics and all the other stuff, we've got the mechanical backup that can operate the stabilizer as well. Power control units, yeah, the actuators, there are multiple types of actuator. The slides are just there to try and shows the different actuators, but all the transfer inputs, the yaw damp inputs, so all the other good stuff's going to be attached in there as well. And all that gubbins eventually is going to lead to an output from the actuator. And the output from the actuator is the thing that's going to move the elevators for us. Anything else we need to say there? Yeah, horizontal stabilizer operated by a screw jack. Again, I think we'll come on to a picture of that. There you go. Yeah, screw jack driven by 2 independently supplied hydraulic motors. There's your motors there. Your screw jack. Won't go too deep into this, we don't need to, but the motors providing power to the screw jack turning, and it'll extend or retract as required. Mechanical trim wheel connected into the system, yeah, from the center pedestal. We talked about that before, the mechanical trim wheel. And that's going to put an input in. Pilot can override the electric motor via the mechanical control. Yeah, turning the trim wheel. It is hard work, but you can do it. Adjacent to the trim wheel, an indicator show the position of the horizontal stabilizer. Side stick controllers used for pitch and roll manual control. And that's our side stick controllers. Yeah. One for the pilot, one for the co-pilot. Yeah. stick themselves installed on the captain and first officer's forward lateral consoles, just forward the armrests. The side sticks are coupled electrically, each one mounted on a gimbal. We'll have a look at that in a moment as well. Mechanical linkages connected to artificial feel units, so we're still going to provide feel even though it's fly-by-wire. It still needs to have that resistance to know how much movement to apply. One pilot wishes to take control. Yeah, the autopilot instinctive disconnect button is used to signal the priority. Yeah. 151, the last paragraph, again, stick your highlighter through there. Yeah, if we've got one pilot wishing to take control of the aircraft, he uses the autopilot disconnect button to say who's got priority. There's a visual indicator to show which side stick has got control, has got the priority. And when the autopilot is operational, the side sticks remain in the neutral position. Yeah, so with autopilot driving the aeroplane, you're not going to get any feedback to the side sticks. They will stay where they are until there's a manual input from the pilot. Again, make a note of that with your highlighter. Yeah, so your side stick controllers. Yeah, going to put the input in. Input to the hydraulic motor. The hydraulic motor again driving the screw jack. Yeah, position transducers. Yeah, again giving feedback and showing the position of the horizontal stabilizer. The no-back brake that it talks about just prevents the air loads moving the stabilizer when it's in its selected position. And nothing else that we need to worry about on there. We talked about all the other stuff about limit switches and mechanical stops, all the other good stuff that we've mentioned. The side stick controller itself, yeah, you've got your priority selection switch, your autopilot disconnect, and that will give priority to whichever controller. Yeah, and there'll be a light on to say who's got primacy. The gimbal, yeah, is that it just allows the lateral and the fore and aft movement. I suppose it's a bit like a posh universal joint, if you like. So the pilot's going to put his inputs in, left, right, fore or aft, and via that gimbal, what's going to happen via two little links, that's going to put a mechanical signal into a transducer, and that transducer is going to convert the electrical signal or the mechanical motion into an electrical signal. That is then whizzed off down to the computer, and the computer then whacks that off to the actuator to get the response to the movement. Yeah, as I say, within there we've got our artificial feel. Yeah, so as we move fore and aft, again the fore and aft movement, moving a control rod. Yeah, converting the mechanical movement into electrical signal, and at the same time we're getting the resistance to that movement to give us our artificial feel. Everybody okay with that? Bingo. Right, we talked about the control laws. Yeah. What happens under normal control laws? Everything's working, and again, just reading through from the notes there, in the example given, the ELACs control the aircraft in pitch and in the normal control law, and they do that by sending the signals to the elevators and sending trim commands to the trimmable horizontal stabilizer. Should we get a failure in the ELACs, yeah, the SECs will take over and provide pitch control and horizontal stabilizer control. Because we've had a failure, that means we're reverting from the normal control law down to the alternate control law. Yeah, so we've gone to an alternative. Should we get a failure in the alternate system, so let's say the SACs drop offline for whatever reason, yeah, we now revert to direct control. And the direct control law is a direct input from the stick to the elevators. Yeah. Complete failure of everything, yeah, means that we're down to winding the handle on the mechanical input hand wheel in the cockpit. So we're putting a mechanical input in. So those are our control laws that we operate to. In real life, there's about 20, 25 control laws, but the ones that we need to worry about, the normal control law where everything is sweet, the alternate control law, if we get something drops out under normal control, drops out, we'll revert to alternate. If we get a failure of all the computers, yeah, we can revert to direct control, which is a direct electrical signal between the control stick and the actuator. And if we lose all that power, we've got the mechanical backup to revert to. Those are our control laws. Yeah. And that's what the system relates to. So that was our pitch system, screw jack, all the other good stuff there. The Boeing flight deck, I was saying about the side stick controllers, what Boeing do, they tend to stick to the conventional hand wheel, but all the gubbins inside is electrical, so we're moving the control wheel, it's generating an electrical signal to the computers rather than a mechanical link up to the control surfaces. Same with the side to side, same with the rudder pedals. Yeah, they're all generating electrical signals. Your speed brakes, yeah, we've already mentioned those. And then on the side of the console, that one's better, see better. We've got the mechanical wheel, should we revert there. Again, more examples of the rudder PCUs. The reason you get the Tornado, because I used to work on them, so know where the actuators live. Yeah, the rudder actuator, again, transfer valve bolted onto it. It's taking in all the various inputs that it needs, and that will result in a extension or retraction of the actuator. Yeah, what they call the taileron. Yeah, which is a slab tailplane that operates both as an elevator and gives us roll control. Yeah, and then your spoiler actuators and the spoiler control module. Again, the spoiler control module taking signals from the computers, relaying those to the spoiler actuators, and they're responding accordingly. Again, on the taileron actuator, you can see the transfer valves there, and the little lever, yeah, that lever, you can see the forward link attached to the actuator position. So as the actuator's moving, it's giving feedback to that link, which is going to nullify the servo input, and that is going to be sending feedback signal to the computer to say, you know, I've arrived where you've told me to be, basically. Again, just more examples. We don't need to worry about them, but just the types of actuator that you might come across on your larger aircraft. The roll control, yeah. Again, we're looking at ailerons. We're looking at multiple actuators. Again, one will be in damping mode, the other will be in active mode, and if we get a failure in the active one, they will immediately swap over. Yeah, roll control provided by one aileron on each wing. Aileron supplemented by the spoilers. So again, working in conjunction. Each aileron, 2 electrically signalled actuators supplied by independent hydraulic systems. Position based on signals from the side stick controllers, processed by the ELAC computers. The ELACs then send those commands to the SECs. Each spoiler surface powered by one PCU. PCUs controlled by servos. Should a spoiler system failure be detected, the spoilers are retracted. Yeah, so they're not going to interfere with anything. 2 PCUs on each aileron. Normally one operates the aileron, the other's in damping mode. If one fails, that will go into damping and the other one will take over and take over control. Position for feedback and monitoring from transducers in the actuator. Autopilot commands received are automatically put into the actuator via the flight control system. And wing gust load alleviation, which we'll talk about later. Basically, if we get a gust of wind, we can use the ailerons to offset the stresses caused by that. Yeah, so your ELACs, yeah, your side stick commands taken in by the ELACs. The ELACs talking to the spoiler computers, and they're sending signals off to the spoilers. At the same time, the ELACs are sending their signals off to the aileron actuators. Yeah. Should we get a failure, yeah, we'll get the reversion to the alternate system. The load alleviation function there, the 2 sets of computers talking to each other, monitoring what's going on and causing the control surfaces to move to react to any gusts that might occur. Ding ding. That was pretty much your roll side of things. Actuators. Again, just it's there just to try and show the architecture. Your side stick controller, your pilot's input into the ELACs. The SAC's in there as well. They're taking the inputs and your alleviation, or your fast-acting computers for your alleviation, and they're sending signals to the actuators, and the actuators are responding to what the computers are saying. And as we said earlier, if it all goes horribly wrong, we've got mechanical backup right at the end. The yaw control is coming from the rudder pedals, and the rudder pedals, again, at the back of them, they've got a transmitter. Transducer, that's the word I'm looking for. Yeah, that transducer, again, talking to the computers, and the computers sending the signals out to the actuators that are attached to the rudder. The computers are also looking at the travel limits for the rudder actuator. We said we need to limit the amount of travel we're giving it. They're also looking at any inputs from the yaw damp gyros. So as the yaw damp gyros kick in, yeah, they sense that onset of Dutch roll, then again there's going to be a correcting signal sent straight off to the yaw damp actuator, which in turn is going to make the main actuator move. Again, you can see little fast-acting computers tucked into the system there. We've got a rudder trim in the system. The trim selector, yeah, flick left or right, and again that trim selection is being fed into the computers. Been put in there. You'll notice we've got the artificial feel unit for the pedals as well. So the more he presses the pedals, the more resistance he's feeling. and that artificial feel for the rudder pedals tends to be a spring. Yes, and the system described, you're controlled by a rudder operated by 3 PCUs, common mechanical input. Input commands from the pedals, from the trim actuator, for the yaw damp actuator. Pedals connected together. Via a summon unit turn connected to the PCUs. Centering spring holds the PCU in the neutral position. If for whatever reason we get a disconnect, it'll just go to neutral and the airflow will hold it there. A mechanical rudder control always available from the rudder pedals. Pedal position signals are sent to the ELACs by the transducer. Pedals fitted with a spring strut to provide feel. 0 force position spring strut is controlled by 2 trim actuators. Manual flight, the pilot can apply rudder trim using the rotary switch there that we mentioned, and the reset button on the rudder trim panel resets the rudder trim to 0. Autopilot engaged, rudder trim automatically applied. Engine fails, the yaw that develops is corrected automatically. Midway down page 158, when rudder trim is applied, it causes the rudder pedals to reposition. So if I've got my rudder pedals, I apply a bit of trim, the pedals will adjust to the new neutral. So the pedals will move when I apply rudder trim. Yaw damp and turn coordination commands do not move the rudder pedals. So if the yaw damp kicks in, the system damping out that Dutch roll tendency will get no feedback through the pedals. Yeah.
Where it will be marked? Which page? Page 158?
Page 158. And it's in the middle of that center. The paragraph that starts in manual flight. Next sentence in, the yaw damping and turn coordination commands do not move the rudder pedals. You found it? Okay, lovely. Nothing else we need to worry about there. Travel limits, a variable stop driven by 2 electric actuators. So as aircraft speed increases, deflection decreases.
Then in the previous sentence, that when rudder trim is applied, it causes the rudder pedals to reposition. It means there is a feedback.
No, but if we're moving the rudder trim, we're moving the rudder position, so that rudder is going to go to a trimmed position, and what happens is the pedals will move to give us a new neutral. So now if I want to apply rudder, I've got full movement of the pedals. It's just when an outside system, something like the yaw damp system, when that flicks the rudder either side of neutral to damp out your Dutch roll, the pedals aren't going to move in response to those outside inputs. You see what I mean?
In the yaw damping, there is no feedback, right? That is rudder pedal. Do not have the rudder pedal in the yaw
damping. The yaw damp. When the yaw damp moves, it won't affect the rudder pedals. You get no feedback from the rudder to the pedals with yaw damp. But when you're applying trim, the pedals will move to a new neutral position.
That means there is a feedback.
Well, it's not feedback. It's just it's just adjusting the position of the pedals. So if move the trim switch, that rudder is going to move slightly either side of neutral, isn't it? Yeah. And what happens when I move the trim, the pedals will move backwards and forwards just to reset a new neutral position. So when I go to move the rudder, I've got full movement of the rudder pedals. When I'm in damping mode, that rudder could be flicking backwards and forwards, yeah, to stop the onset of control. If it's doing that, there is no feedback from the rudder through the pedals. The pedals won't move. You wouldn't be able to. You wouldn't know, apart from an indicator, that the yaw damp's actually working.
Okay, Jim. Thank you.
Okay.
Oh,
Nothing else we need to worry about there. Done that. Yeah, again, just simple layout. Yeah, you've got your trim switch, the trim, the rudder trim, inputs into the computers, what's calling the flight augmentation computer here. Those computers are also looking at the inputs from the ELACs for your because your ailerons and your rudder are interconnected for when you're putting in turns and what have you. So as you're turning the aircraft, as you're banking the aircraft, there's going to be a rudder input as well as a lateral input. Travel limiters to prevent us moving the rudder too far. The yaw damp, yeah, which is independent of the other bits, putting yaw damp inputs in to prevent the onset of Dutch roll that we talked about, and your trim inputs will be fed into the actuators as well. The centering spring giving us feel, but if we get a failure in the system for whatever reason, that centering spring will bring the rudder to a neutral position, so it's not sticking out into the airflow. Just the mechanical feed, and we saw this the other day. Yeah, your rudder pedals left and right, down to your cable inputs along the length of the aircraft. The cable inputs back to the quadrant at the rear. From the quadrant at the rear, we're going to put in inputs to the rudder actuators. If you notice that picture there, yeah, we were talking about the crush struts the other day, yeah, the stuck servo detectors, and that's where that picture of the stuck servo detectors came from. So if the servo sticks, again, that's going to put in a warning light in the cabin. The pilot will take that system offline, and the other two systems will carry on operating the control surface. The duff actuator will just go into damping mode. And again, in the rudder system, yeah, we've got our yaw damp, yeah, yaw damp actuators, and the yaw damp actuators again via the linkage putting inputs into the main actuators. We've got a trim actuator, trim screw jack, moving the moving the rudder on demand from the trim switch. I'm not going to go into the ins and outs of the actuator in damping mode and active mode. We don't need to, and it just wastes a lot of time. Yeah, the spoilers, let's just make sure we're on the same page. Yeah, the spoilers, page 163. Yeah, movement of the control surface by the actuator, servo control pressurized, and then it'll take you through step by step what's happening. Basically, we're going to turn the system on, we've got hydraulic pressure coming in. And that hydraulic pressure via a servo valve is going to move the actuator in or out. Yeah. While it's in active mode, it's responding to the signals. We've got the transducers there that are giving feedback to the spoiler control computer. So computer says move. Yeah, the input, yeah, by the servo causing the servo to move. Yeah, and that's going to direct fluid one side of the actuator or the other. If we go into damping mode, yeah, what happens is the mode selector will go from the active mode, it'll go into a sort of neutral position. So now fluid, as the other actuator takes over, fluid will just pass around the actuator and go back off to return. There's no what's the word I'm looking for? The active one will take over. The actuator that's in damping mode will just get dragged backwards and forwards with it. Yeah, but if you want to have a read through of how it all operates internally, please feel free. We don't need to go that deep into it, and it does, as I say, become quite complex to try and explain. Yeah. If I had the time and you were ab initios, I'd do it, but we don't need to worry. Fly-by-wire system, yeah, many items classified as LRUs, line replaceable units. Yeah, so you might be able to change various components actually on the actuator in situ, which saves an awful lot of time. Yeah. Load alleviation or active load control. Yeah, what's happening with that? To reduce the loads that are being felt on the wings, yeah, we can use the fly-by-wire system to reduce those loads, provide aerodynamic forces to oppose twisting and bending motions, use the control surfaces. So if an upgust comes under one wing starts to bend upwards, yeah, we can nullify that by using the ailerons and spoilers to reduce the lift on that wing. Yeah, so if we get a gust of wind hits us under the wings, yeah, the aircraft will sense that. It'll put the ailerons or the spoilers up, and that will spoil the lift over the wing, which in turn is going to relieve the bending stress that's being felt at the wing. Yeah. Active load alleviation requires the use of special form of AFCS computers with sensors dotted about the place that are going to sense the movement of the wing due to those gusts and what have you. So your benefits: reduction of structural loads, improves your fatigue strength because you've not put that strain on there, and it makes your ride more comfortable. So there's yeah. Can also reduce structural loads during manoeuvres. So one method is to use the inboard flaps to increase the load on the inboard wing portion when using high lift manoeuvres. So if we've got a steep turn, again the fly-by-wire system can operate the flaps automatically just a wee bit to take that stress off the aircraft. Nothing else we really need to say there. So your active load control, yeah, just bear in mind what it's for, and it's going to move the flight controls to oppose the forces being applied by wind gusts and all the rest of it. No, can't say anything else there. Right, very, very quickly then, because we've done most of it, we'll have a quick look at control system maintenance. because I've got to. But maintenance, the first thing it talks about is mass balance. And we looked at mass balance the other day, and we said that the mass balance operation is there to prevent flutter. Flutter, the rapid oscillation of the control surface around its hinge line. Very important that we also make sure that the tabs haven't got any flutter associated with them. So just that's where we're meant to be. Just trying to find the page number. The top of page 168. In the absence of any data from the aircraft manufacturer, the free plate at the trailing edge of the trim tab should not exceed 2.5% of the average chord of the tab. We did highlight that the other day, but again, stick your highlighter through it so it's stuck in your mind for if it does appear in the exam. Just below that, should it be necessary to repair or repaint a control surface at any time, it's essential that the mass balance is checked in accordance with the AMM. So painting or repairing a control surface, mass balance is rechecked. It then tells you how to do mass balancing, but to my way of thinking and everybody else's, it is a crucial maintenance operation. So you're going to be following the maintenance manual step by step. So the idea of giving you this is just to give you an idea of how mass balancing is carried out. We don't need to remember it. So it describes how we're going to do it. Balancing the thing, the mass balancing procedure, repair manual, give you the moments, take the thing off the aircraft, work out where it's going to be done, don't worry about any of that. At the bottom of page 169, the last paragraph, for repair a control surface which has been stripped down to the bare metal from an overpainted condition must be rebalanced after repainting. So over a period of years, all the touching up we do, the paintwork gets thicker and thicker and thicker. So when they strip the aircraft down for an overhaul, if the paint has been removed, if it's brought back down to bare metal, we need to rebalance it once it's been repainted, because there's quite a bit of weight associated with paint, believe it or not. So that was your mass balancing. Control system inspections, we're not going to get collared for that, and it's common sense. So we're not going to worry about that too much, the sort of things that we're looking for, where we're looking for it. Make sure your bearings all line up, all the rest of the good stuff. System rigging, we'll need to rig the systems from time to time. When are we going to do that? When the aircraft's been manufactured, when the maintenance manual tells us if we change a component, if we get a flying fault report, heavy landing. So all the rigging procedures depends what's happened to the aeroplane. And the maintenance manual is going to tell us how to do the rigging. It's going to tell us how to set everything up. Big thing there, refer to the AMM. When it talks about a sense of movement check, freedom of movement check, the freedom of movement, that there's nothing preventing movement of the control surface. The sense of movement, making sure it moves the right direction. I've actually seen it where somebody cross-connected a cable. So when we push the stick forward, we wanted the nose to go down. We wanted the elevons the elevators to go down. to bring the tail up, but the elevators were actually going up. So if we'd allowed the aircraft to carry on, we'd probably have lost it. Yeah, and it was because somebody had cross-connected a control cable. So again, what to watch for, make sure that the sense of movement is correct, as well as the range of movement, as well as the freedom of movement. Yeah, different devices that we can use to hold things in the neutral position. Again, they're very much aircraft dependent. Rigging pins are a favourite. Yeah, pins that we put in at various points in the control system to hold everything in position. Only thing I'd say there is if you've got rigging pins in, again, you're following the maintenance manual, but remember to take them out before you move the control system, especially if it's hydraulically powered. Once those pins get bent in position, it really is a pain to get the bloody things out. Yeah, so be very careful that they're removed before you apply hydraulics. Cable tensions, we know all about that. Sense of movement, freedom of movement. Don't need worry about any of that. Yeah. Range of movement, how far up and down we're going. Loose article checks, once you've finished any work anywhere on the aircraft, we always do a loose article check. The amount of times we've found things lying about that people have left in the aeroplane, and if something gets caught up in a control run, it can be devastating. A guy I used to work with, he moved up to a company in the north of Scotland. They had an aircraft coming from Lithuania, and it declared an emergency. The pilot couldn't move the rudder at all. It didn't matter how hard he tried, couldn't move the rudder. He landed the aircraft safely, and when the guys took the panels off to do an inspection, they found a big screwdriver wedged in the control run. Yeah, so Dave, the guy that found it, he was on a winner because he got himself a new screwdriver. The guy that had left it in the aircraft, I think, was severely reprimanded. Yeah, so always carry out a loose article check. It might not have just been you that's been working in there. It could have been somebody else looking in and has left something lying around. And the other thing, anytime we disturb a control system, we need to carry out a duplicate inspection. The duplicate isn't there to catch you out. It's not there to say that you don't do your job properly. The duplicate is there to make sure that if anything has been missed, it gets picked up before the aircraft goes flying. Yeah, they are a really valuable tool, a second set of eyes. If you've been struggling trying to set something up for days, you eventually do it. Sense of euphoria, it's easy enough to forget to put the split pin in the nut. Somebody independent of the job comes along, has a look over, you've missed that split pin. Oh, brilliant, thank you. Yeah, so it's not a reflection of your workmanship or your ability. It's there purely as a safety precaution to make sure that we find anything before it becomes too much of a pain. Yeah, just the last little bit on that. Always refer to the AMM. Yeah, warning notices around the aircraft if you're moving things. If you've tripped CBs, all that, make sure it's recorded. And reset before we go flying. Once you've finished, make sure that your accumulators are discharged. And then it just goes through about checking cable tensions, all that sort of stuff. We don't need to worry about that. Yeah, secure everything, finish everything. Rigging pins kept under strict control so that we know where they are, so they're not left in the system. Putting them in, taking them out, yeah, it should be recorded on your worksheet. It's always a good idea, even if the company don't require it. Just put an entry: rigging pins fitted at point such and such, and then at least that way they're not going to get left in the aircraft. Sense check, moving the right way. We've talked about that. Freedom of movement check. Yeah, make sure it goes through its full range and that there's nothing interfering with it. Range of movement, how far it needs to move, make sure that that's all in limits. Control locks, check that they're engaged and disengaged properly. Yeah, nothing there. Loose article check, duplicate inspection. All parts of the flying control system classed as vital points. Page 176, when it talks about duplicates, any vital point requires a duplicate. A vital point is any point on the aircraft in which a single incorrect assembly could cause a loss of the aircraft. Stick your highlighter through that, what a vital point is. And then it just tells us what a duplicate check is. And how to carry out a duplicate. And make sure that we sign up for everything. Done that, done that. We've done that, we've done that. Fault finding. Again, following the troubleshooting procedure in the manual, but it just goes through the best ways to hunt for a fault. Yeah. And what some of the causes might be. That causes an aircraft might be reported to fly one wing low in general terms, looking at what might cause it. Yeah, just, I'm not saying highlight that, but have a read through just to see some of the things that might cause an aircraft to fly one wing low. Got an aeroplane flying over my house now. Checking all that, nothing there. Yeah. It's just giving you a rough idea of things that might cause you flying control problems. We don't need to highlight them, but just as you're revising, just have a quick look through, just so you know the little things that might cause problems. Right, I'm at that 10:25, so 20-minute tea break. So that'll be 10:45 my time. 20 minutes time for you guys, because I haven't got my telephone here. So we're going to have a cup of tea there, and then we'll have a look at high lift devices after tea break. So I'll see you in 15 minutes. 20 minutes.
Okay.
Kettle needs to boil. All right. Okie dokie. All right, got everybody back. Oh, nicely warmed through with a cup of tea. Before we kick on then, anybody got any questions on anything that we did before break? No? Okay then. So what we're going to do, we're going to have a look at the high lift devices on the aeroplane. High lift devices, your leading edge devices, your trailing edge devices, and the first section is the trailing edge flaps. And as it says in the notes there, that your large, heavy transport aircraft require large flap area to allow them to take off and land at low speeds. Shortens the takeoff runs, shortens the landing runs. So we've got to make sure that the flaps are there, and so we'll give them an alternate power source should we get failures in the prime sources. We also need to protect against asymmetric flap. Yeah, the asymmetric flap is where one set of flaps travels further than the other. And effectively, they're going to act similar to ailerons. They're going to induce a roll in the aeroplane. And if we allow them to travel too far, then the roll might well become unrecoverable. So we limit the amount of asymmetry that they're allowed. Also, with the flaps, you're putting large surfaces down into the airflow. So each position of the flap is limited to the airspeed that the aircraft is travelling at. So for each position there should be a placard next to the flap selector saying what the maximum airspeed is for each particular position. Yeah, high lift devices, yeah, just showing the difference. It's a nice picture of the slats there. You can see the slots have formed. Yeah, your extension flaps, so as they're extending, they're increasing the surface area of the wing as well as the camber of the wing. And again, nice picture of your trailing edge flaps. Propeller-driven aircraft, so leading edge devices not required. Your flap selector. Yeah, flap selector, and alongside the flap selector there will be an indicator telling us the position of the flaps. be it leading edge or be it trailing edge devices. Yeah. We normally refer to it as degrees of flap, but it isn't. It's units of flap. And again, depending on the airspeed that we're travelling at, depends on how many units of flap we can apply. The flap selector, a mimic handle, looks like a flap, feels like a flap. Yeah. Handle connected to AC electric motor or hydraulic motor. Movement of the flaps. Take off warning. Flap selector handles move to the drive motor runs. Flaps go to selected position. Any leading edge high lift devices normally travel in conjunction with the trailing edge flaps. Moving the flap selector will initiate the movement of both. Basic flap system. A drive unit, a torque shaft, which is just a shaft that's going to spin round. As that shaft's spinning, it's attached to screw jacks. And as the torque shaft spins, the screw jacks will drive the flaps up or down to their selected point of travel. Protection in there. We'll have a look at that. Hopefully, we'll get that. Protection. We're going to have over travel stops. They're normally within the drive unit, and they're going to prevent the flap traveling too far up or too far down. Limit switches. Stops the motor when we've reached the limit. So we've got a up limit and a down limit, and then the drum switch is it's an old type of switch, I've got to confess. There's a drum switch which turns the flap off at its normal point of travel. Reverse the direction of the flaps. The drive motor's got to be reversed, but with the motor being so relatively large, it's got to be stationary before you can make the opposite selection. And I can't remember whether it was in a mock exam or the real one, but I have seen a question along those lines, about drive motor for the flaps got to be stationary before the selection can be reversed. So before reversing the motor, it's got to be...
On which bit, sir?
That's 183. So what we got then? You've got your motor, you've got your electric supply via CB to your motor. You've got your protection switches, your asymmetric flap, your over travel up and down. If those are hit, they'll trip the protection CB, and our selector switch. So we'll make a selection, flaps up. The drum switch, half of it's at the. It's a horrible thing to try and explain. I've got a better picture of a drum switch. Let's just have a look. This is an example of a drum switch, and you've got a drive coming in, and inside you've got little contacts. So depending on the selection you've made, as the drive is rotating, it'll make a contact within the drum switch. The other half of the drum switch is at the selector end. So we'll say, right, I want 40 units of flap. We'll select that 40 units of flap. the control switch part will start turning, which is going to drive this, and when we get to the 40 units of flap, the switch will trip and it'll turn the selection off. It's a, as I said, bugger to describe the drum switch. It's a circular contact disc divided into 2 equal halves by an insulator. Yeah, there's brushes in there, and they contact the disc at 180 degrees to each other. So when the flaps are selected down, mechanical feedback rotates the drum switch anti-clockwise, it says, until the switch contact is on the insulation and the flaps stop. And that's repeated with each selection. Yeah, so during the retraction, reverse takes place. And the drum switch is normally mounted on the flap motor gearbox. So I don't know whether you guys can see me. If you can imagine that's your drum switch, the 2 halves fitted at 180 degrees to each other. So as they rotate, yeah, there's insulation on each of the contacts, and as we go through each of the contact points, the thing stops. Then it'll start again until it reaches the desired position. I've got to be honest. I've never come across the drum switch in the setup that's described. I've also had a word with a few of my colleagues about it, and I've been told that it's only found on older types aircraft. There's most modern aircraft have got different signalling systems to the motor to drive it backwards and forwards. So I'll apologise because I'm not speaking from full knowledge on the layout of a drum switch, but there you have it. We've just got to run with what the notes tell us. So the drum switch is basically our selector. We're going to select up or down. Yeah, we select up. The drum switch will rotate, and the contacts will break when we get to the desired point, essentially. Limit switches are there to stop us going too far, to go out with the I won't say over travel, but we're going to cut the system off when we get to the right point. We've got a motor stationary detector in the system. That's to make sure that before we make another selection, that the motor is stopped. Yeah. If I want to turn it back, yeah, we've got the reversing contactor. Yeah, and away we go. So let's say your drum switch, yeah, you select up. That will then run a signal to the flap motor. And as the flaps are moving, yeah, we've got the position feedback, the drive shaft coming into the drum switch, so that when the 2 halves get to the required position, that the signal's interrupted. Can't say much more than that on there. Anything else we need to say? Normal limits controlled by the drum switch. Limit switch is mounted on the flaps, prevent extreme up or down travel. They'll stop the flap motor, and then over travel switches in the drive unit kick out the protection trip if we go over the point of the limit switches. The clutch torque switch on there, yeah, the switch stops if the flaps have excessive load on them. The asymmetry detector, yeah, any difference between the left and the right flaps detected by monitoring the torque tubes. We'll look at that in a few minutes. But if we detect an asymmetry, that will trip off the system, and it can't be reset till we're on the ground and we've carried out our investigation. Yeah, motor brake prevents the motor rotating when it's switched off. Yeah. Protection unit receives inputs from the various points. Any inputs will operate the protection trip, stop the flap motor from running. The drum switch I've just tried to explain very, very poorly. Drum switch normally mounted on the flap motor gearbox. Yeah, so as the flap motor gearbox is travelling, it's sending a feedback to the drum switch. The drum switch, one half selected from the cabin, and when that feedback reaches the desired position, it'll stop them travelling. Flap indicators shown on the centre console, calibrated in, like I say, it says degrees here, but we talk about degrees of flap, but generally, technically, it should be units of flap. If you talk about degrees, then nobody's going to worry about it, but it should be units of flap. If you get the system tripping off, then you're going to get a warning caption. Like I say, that was your drum switch. Your selector will put an input in one side, and your feedback is rotating. These little switches, there's insulation on one half, and as the insulation travels around, it breaks the signal and the flaps stop. Yeah, your indicators showing what position the flaps are in. Fully up, yeah, so many units. Again, just a different version. So the analog version's a lot easier to read. It's more instinctive than the digital version, if you like. But you can see on that one, it's got the limits next to it. What you can fly to with the various units. Normally, you'd have a placard next to the indicator, and some flap indicators, if you've got the leading edge devices fitted, yeah, the leading edge device position will be noted on the indicator as well. Diddly dee, diddly da. Yeah. Large transport aircraft, yeah, normally use a hydraulic motor to operate the flaps. If the hydraulic supply fails, then we've got an alternate power source, either electric motor or another hydraulic system. Yeah. Selecting alternate flaps unlatches the prime hydraulic motor, so any hydraulic lock that might be in there is released back to return. So the alternate system will drive the flaps at a slower rate, but the main hydraulic motor won't impede the movement, if you like. Yeah, so that one just showing your power unit. Yeah, we've got a alternate power source should we need it feeding in. Your drive rods, your torque shafts rotating, and as they rotate, they're driving a screw jack. In this case, the three-piece flap. Yeah, but the screw jack's driving them all, and the flaps running tracks. Again, we'll look at those in a minute. Position transmitter on the end of the torque shaft, and that's those position transmitters are sending a signal back to the gauge. Normally, the two pointers would travel in unison, yeah. But if we get an asymmetry, yeah, the transmitters are going to be sending the signals back to each of the gauges. If we get an asymmetry, yeah, once those indicators, the needles go beyond a certain point, split beyond a certain point, then the system will trip off and we can't reset it until we're on the ground. Yeah, so that's your basic system. Anything else in there I need to mention? Not really. Yeah, controller, that's telling us which way to go and how much we want to go. Taken from the selector in the cabin. The drive unit, the power unit, is the thing that's driving the torque shafts to transmit the travel. Yeah. Tick, tick, tick. So I'm reading through the notes as I go, just to make sure that anything that's recognisable I've pointed out to you. Yeah, each flap driven by a torque tube. Yeah, the torque tube attached to your screw jack that will drive the flaps up and down. Torque limiter incorporated in each actuator gearbox. So in the event of a jammed flap, the torque limiter absorbs any excessive torque till get to the point where the motor is going to stall. Torque limiter stalls the power drive unit if the applied torque is 20% greater than the normal operating torque. And that's a figure that jumps off the page at you. So top of page 188, yeah, just the torque limiter stalls the PDU if the applied torque is 20% greater than the normal operating torque. And the way it does it, it's just a little interconnecting device. Yeah, two clutch plates engaged with each other. We've got the output drive, input drive. As the shaft's rotating, if we get a shall we say, jam in one side, yeah, the shaft's going to carry on rotating. The other side's going to remain stationary, and what happens is the torque causes these ball bearings to ride up in a cam. Yeah, so under a normal load, yeah, everything's sweet. If we get an abnormal load, a sort of torsion, excess torsion force, yeah, these balls are driven up the cam, and they will disconnect the two halves of the clutching unit. Yeah, so it'll overcome the spring. It'll twist the two halves apart. So that's our torque limiter. Is that somebody trying to talk to me? Hello? No? Okie dokie. Right. Rattle on then. Yeah, so you talk. Hello? No? That's your torque limit, and it's just there if we get a jam in the system, it's going to allow the transmission to disconnect itself, the input shaft to continue rotating, the output shaft remains stationary, and that prevents damaging the system. Yeah, and it's just those little balls riding up in the little cams. Transmission system may have a no-back brake in it, and that's to prevent the air loads from pushing the flaps back up. Yeah. Power applied to retract the flaps. The power unit overcomes the brake, allows the flaps to retract. Doesn't oppose the extension of the flaps as it works on a ratchet. Again, we'll have a look at that in a minute. The no-back brake. Position transmitters fitted at the extreme end of the left and right transmission runs, and they're sending the electrical signals to the position transmitter. As we said, they normally travel in unison, but if they split beyond a certain point, then it'll trip the system off. And again, your position indicator telling you what position your flaps are in. Yeah. Yeah, so your drives screw jacks, yeah, and the screw jacks are going to rotate and drive the flaps down. The flaps carried in flat tracks. Yeah. Anything else I need to say about that? Yeah, that's a better picture of a track. Yeah, screw jack attached, and the flap itself via rollers. Yeah, rollers engaged with the track, going to drive the flap to its selected position. when it talks about jack screws, I've always known them as screw jacks, and that's what we're going to call them. I think jack screw is more of an Americanism because they like to be different. Any problems there? Yeah, the movement of the flaps as they start to travel. Yeah, they'll be carried in the track, and there's a series of push rods making sure that everything travels in the right sequence. Yeah, so there's a sequencing arm there, and the sequencing D10 flap will travel to one position, then it'll move on to the next one, and so on and so forth. Yeah, in this case, you've got your 3-position or 3-section flap: the fore-flap, the mid-flap, the aft-flap, and as the thing's travelling down, it's going to extend out. Yeah, the sequencing arm, the push rods, making sure that everything goes in the right order, and as it travels, the aft flap's going to go to its full extent, travelling on a track in the mid-flap. Yeah, and then the mid-flap's going to travel. And as the mid-flap travels, dragging behind it is going to be the fore-flap, which will again go to its selected position. And again, with the flap sections, you're forming the gaps through them for the airflow. Ta-da, ta-da, ta-da. Yeah, so your transmission, 2 transmission assemblies for each flap. Transmission assembly enclosed in the flap track fairing. What we've got is the transmission gearbox, universal joint, ball nut, and the screw jack. Each gearbox incorporates a torque limiter, so if we do get an over torque, it'll stall the drive unit, stops rotation of the drive shafts until everything slows down. So if you do get a jam, it's just disconnecting the drive to prevent any damage. The screw jacks, have got up stops and down stops, so we're not going to over travel. The ball nut, it says contained in a gimbal, that just allows for angular motion as the flaps are traveling. Obviously the jacks are going to need to adjust their position. Power drive unit rotates a series of torque tubes which drive the gearboxes, which turn the screw jacks. Your transmission, as it says there, we've got the input shaft. That's going to be turning away. As that's turning away, that torque limiter that we've just seen. So you've got your input shaft as that's rotating. Going to drive the output shaft via a series of gears. So if we do get an over torque, this thing's just going to ride up on the ball bearings and disconnect itself, and that's going to prevent any output to the output shaft. Obviously got a bit of oil in for lubrication. And there's not a lot else to say there. Yeah, the flap tracks. Fore flap, mid flap, aft flap. The fair with the wing when they're retracted and form slots when they're extended. We've said that. The run-on carriage assemblies. Yeah. Ting ting ting. No, nothing there that we need to worry about. Yeah, that's just showing us how they're stored. The three flaps. You can see the push rod there. So as we select the flaps to extend, flap's going to start travelling. You've got your roller device. That's going to run down the track. As that's running down the track, the push rod's going to make sure that the aft flap extends as the mid flap's coming down, and then once that's happened, as the as the mid flap gets to position, it's going to pull the fore flap into its selected position. Yeah, and the sequencing device, yeah, will make sure that that happens. When it talks about the day tents, just little indentations to make sure that we travel to the right position. Picture there, yeah. So we've travelled the carriage travelling down the track. Yeah, as we travel down, yeah, the rod extending the aft flap. As we said, the mid flap travels, and then via the carriage there, the fore flap goes to its selected position, and somewhere on there, which you can't see now, is the day tent to make sure that we don't over travel. Anything in there? Right. Yeah. Tracks support the flap, and a pair of rollers. Rollers guide the flaps as they move on the tracks. Side rollers prevent the lateral movement. Sequence carriage assemblies support the flaps on the tracks. Toggles lock them to the main carriage assemblies. Don't need to worry about any of that. Don't need to worry about that. Aft flaps supported on flat rails mounted inside the mid flaps. Connected to the mid flaps by a system of cables and operating rods, which allow the aft flaps to move away from the mid flap as they extend. Retraction of the flaps is the reverse of what we've just looked at. To prevent turbulence, reduce drag, the flap track fairings cover each track. Those big fairings are sometimes referred to as bolts. I'm not sure that it mentions it in the notes later on, but if you see the term bolts, it's just the aerodynamic fairing that covers the flap tracks. And again, nothing there for us to get our knickers in a knot over. Yeah. The asymmetry detection system, yeah, asymmetry detection we definitely need, yeah. So on the extent of the transmission, left hand and right hand, we're going to have position transmitters, and the position transmitters are feeding back, in this case, to the position indicator. The flap positions should be the same, near enough the same. Yeah, nothing between them. As the flaps travel, yeah, the gauges will go together, the needles will go together. If there's an asymmetry, the needles will start to split. Yeah. The asymmetry detector will look at that. Yeah, it'll detect any difference between the positions of the flaps, and it will send out a signal that will lock the flaps up. Yeah, so we now don't get any further travel from the flaps to prevent us getting into that out of sync situation. Yeah. So at the same time as locking the flaps up, it locks the hydraulic motor up. And it puts on a warning caption on the flight deck. That's a very basic system. Yeah. It says there are various methods of sensing, and that dual pointer is one of the methods. Yeah. Probably a relatively common one, even though it's old. It's simple. It works. Yeah. So as I say, it shuts them off once symmetry's been detected. And I'm looking for the figure. I'm sure it's something like, if there's a 5-degree difference between them, that the system trips off. But as we go through, keep looking for that figure. Yeah, I've got it in my head. It's 5-degree difference, but I can't see it as yet. So as we're going through, just keep your eyes open. That's all that little lot about. The trailing edge flap bypass valve connects the flap hydraulic motor and the return ports to prevent the pump from running during the operation of the alternate system. So if the drive unit, let's say, suffers a hydraulic failure or whatever, we need to operate the alternate system. Yeah, the bypass valves allows the disconnect of the prime system from the alternate system. Yeah. Valve says the electric motor operated 2-position valve containing 3 connections, hydraulic lines, extend the flap control valve and the flap motor. Valve normally controlled by an alternate flap arm switch. So if we get a failure in the flaps, it's not an automatic changeover. Yeah, the pilot will get the warning light. He'll select alternate flaps. That will send a signal to the bypass valve. The bypass valve will then isolate the prime power source from the alternate power source. Yeah. Downline from the flap control valve blocked, flap hydraulic motor ports connected together to allow circulation of the fluid within the motor, so it doesn't have any effect on the operation of the alternate system. With your flap emergency, normally we're only going to select down. Yeah, some aircraft you'll get both, but what we're going to do on this one is get the bypass valve. Yeah. So your normal system, yeah, works normally. Your pressure and your return, your upline, your downline. Which way we're going? If we get an emergency situation, yeah, the pilot will select the armed. Alternate armed switch. That'll operate the bypass valve. The bypass valve will move over. It'll just cross connect everything, so that the main selector, yeah, is just put in a neutral position. The bypass valve then will make sure that the power supply from the prime source is isolated. It just circulates within the main selector, and then your alternate, yeah, in this case the electric motor, the alternate system can drive the flaps without any interference from the prime source. Does that make sense? It's not particularly good, but what's happening? Yeah, that just goes to, like say, the null position. Yeah, and your feed goes straight in and straight back down to return. Ding. I've got to be honest, I'm not sure why that's appeared in there, but very good sketch. Right. So that's your bypass valve. Your bypass valve purely there to disconnect the prime source of power should we need to select an alternate source. We're selecting the alternate source by arming the alternate flap switch. Yeah, moving the alternate flap switch to arm applies power to position the valve to bypass. Downline from the flap control valve is blocked and the motor ports connected together and allows fluid to circulate within the motor. If we go to off, yeah, the bypass valve will go back to its normal position. Not likely to do that in the air. If you've got an emergency with your flaps, you want your flaps in the right position. You want your aircraft on the ground as soon as you can. However, flap asymmetry shut off relay energized to move the flaps or the valve to bypass and stop flap operation by the hydraulic motor when the when the movement isn't symmetrical. Yeah. So if we get an asymmetry, yeah, the bypass valve will shut the system off as well. Yeah, we'll go into the bypass mode, and if we get a cable problem, again, that'll isolate us. Yeah. Your asymmetry, yeah, the asymmetry test panel provided in the avionic equipment bay for testing the protection circuit. Test switch, green test light are used. Test switch allows us to test the asymmetry sensing capabilities. Yeah, and we can test up, test down. Yeah, and that will cause the pointers in the gauge to split, and the pointers in the gauge splitting is going to trip the system. Yeah, the green light will come on to say that we've gone to the bypass position, and during hydraulic operation, the flaps, should the bypass valve move to bypass, the flaps will stop moving. Brilliant. If you do get an asymmetry, you're going to get a warning light on the CWP. So that's your flap indicator. Yeah, as your flaps are moving, the pointers should be together. If you get that split in the pointers, it'll trip the system off. You test that in the avionics bay, just a little box. Yeah, flick left, flick right. It'll feed in an asymmetry into the system. Yeah, and if the system's tripped, goes to bypass, the green light will illuminate. The electric circuit, we skipped past earlier, but as I'm not an electrician, I'm not going to try and talk through electric circuits, because I'll just look silly. Schematic and bypass, picture in the notes. What's happening there? We've already looked at that, the block diagram. Another type of asymmetry detector, yeah, uses a position transmitter, an asymmetry brake, and an asymmetry transducer at the outboard end of the flap drives. Pardon me. They provide flap position inputs to the position indicator in the cockpit. If the asymmetry brakes are used to stop the flaps in case of a transmission overspeed, or if we get an asymmetry. Symmetry transducers provide flap position inputs to the symmetry comparator. What that's saying essentially is that rather than having the split gauge, there's a transducer at the end of the runs, and that transducer is measuring the positions of the flaps by the I'm telling you, I'm getting Alzheimer's. I think of a word and then I can't remember it to say it. Yeah, it's monitoring the signals sent from the drive shafts, and the signals from the drive shafts should be the same. They go into a comparator box, and the comparator is just looking to make sure that the electrical signal that they're sending is the same on both sides. If there's a discrepancy between the two, it'll assume an asymmetry, and it will send a supply to the drive unit to cut the drive unit off. Yeah, we talked about the power drive unit, and in there the bypass valve. If that trips, the hydraulic motor will be taken out of the equation. If it's an asymmetry, the drive unit is shut down. So we haven't got an alternate power source. Yeah. Should we get an asymmetry, the comparator stops the power drive unit and transmission by applying the asymmetry brakes. Symmetry brakes prevent the shafts from running. There's also an overspeed governor in there, solenoid, and a trip indicator. and nothing for us to worry about there. If we get an overspeed, if the overspeed governor detects an overspeed, this is the combined unit. So it's got position transmitter and the asymmetry drive transducer. Just two little gear wheels. And if we get that's measuring the speed, and if the two signals in the comparator box don't match up, then the system will trip off. The overspeed governor, provisions for externally mounting the position and asymmetry transducers, asymmetry conditions sensed. The asymmetry comparator energizes the solenoid on the brake unit. So there's a solenoid there, allowing the rocker arm to permit the springs to apply force to the brake disc, and at the same time the trip indicator extends, saying that the brake has been tripped. So as the solenoid energizes, it's going to apply the brake, and that's going to stop the output to the drive shaft. Once the brake's on, the overspeed governor has a similar sort of function. If the shaft's travelling too quickly, there's two little flyweights on here. Centrifugal force will move the flyweights, and that'll allow the brake to be applied as well. Again, we don't need to go too deep into the internal workings. It's just to give you an idea of what's there. What we need to know is if we get an overspeed or if we get an asymmetry, the system will shut down effectively, and it can't move anymore. So overspeed, in the event of a mechanical overspeed, the governor flyweights expand, force the rocker arm roller off the disc brake, applying brake pressure to the input shaft. Spring force keeps the brake set and extends the trip indicator. When operated, the system can only be reset on the ground. System self-monitoring and will put a fault light on in the cabin should there be a fault. So asymmetry comparator stops the power drive unit transmission by applying the asymmetry brakes. Symmetry brakes, the rocker arm and the roller, trip spring mechanism, brake discs, position transmitter, and the asymmetry transducer. So your position, asymmetry transducer drives. Mechanical overspeed governor, we mentioned that. Symmetry is detected, sensed. The comparator energizes the solenoid on the brake unit, allows the rocker arm to permit the springs to apply force to the brake disc, and at the same time that trip indicator extends. So again, sensing.
So in the figure there was dual solenoid. Why we need dual solenoid, sir?
I didn't understand a word of that. Sorry.
Sir, in the figure there is the dual solenoid, sir. Dual.
Yeah.
Why is there two solenoid in the system, sir?
Why is a dual solenoid? You've got one for your asymmetry, and if you detect an asymmetry, that transducer, the solenoid's going to operate and allow the brake to be applied, which will stop the shaft turning. I'm not sure if I would say that you've got a dual solenoid just in case you get a failure in one. Okay. Would be by my guess there. Yeah. Yeah. If you get a failure in one solenoid, you don't want to get into an asymmetry condition. So by having the dual solenoid, you've always got that backup then.
Okay, sir.
Which
Okay.
would be my guess.
Okay.
Yeah.
Okay, sir.
Okay.
Okay, sir.
Yeah. Faults. Yeah. Looking at symmetry detection. The fact that the solenoids have operated, putting a warning light, failures within the comparator, and failed transducers will give us a warning of those. Yeah, so that's your transducers. Yeah, looking at the comparator, applying the brakes and cutting off the power, the drive unit. What else we've got there? The flap handle. We've got a cable brake detector in the circuit. The load limiter. Yeah. I think we mentioned the bungees later, and the main power and the alternate power supplies, screw jacks, and your torque limiters in the system as well. But yeah, simple circuit. The mechanical asymmetry protection. Yeah, it's very clever. Yeah, from the left hand and the right hand flaps, there's just a little cable operating a drum, and on the bottom of the drum there's a bevel gear. Between the bevel gears for the left hand and the right hand, little idler, and connected to the idler is a link to the flat motor valve. If we get an asymmetry, yeah. If one's travelling faster than the other, yeah, that idler is going to start to rotate, and as it rotates, it's going to move the linkage to the control valve, and that in turn is going to cut the flaps off. Yeah, so symmetrical movement, both the loops will rotate at the same time, so the idler will just turn on its bearing. It's not going to move at all. If we get an asymmetry, yeah, the bevels will rotate in opposite directions at different rates, and so now that idler is going to start moving round, and it'll, via the link arm, it'll trip the system. Yeah. So asymmetric failure, any part of the drive system is detected, it will trip off. It's a very clever little device, that one. Yeah, for your smaller aircraft. Again, just showing the drive, showing the symmetry bits. Cable brake detector, we looked at that the other day. Right, the flap load limiting system, yeah. Should the flaps be lowered at higher airspeed, serious structural damage could occur. To prevent that sort of damage, the drive systems have a load limiter fitted in them, and that prevents the flaps being lowered at excessive airspeed. If the flaps are fully down, yeah, there's a signal energizes a solenoid in the flap drive unit and causes the flaps to partially retract. Once we've reached a suitable speed, the flaps will deploy again. Yeah, so via the air data computer, yeah, I'll send digital word for the appropriate airspeed to the ARINC 429, whatever that is. Needn't worry about ARINCs, but what we the ADC monitoring the airspeed. If we lower the flaps at too high an airspeed, yeah, the system will retract the flaps slightly. Once we're down at a suitable speed, then the flaps will extend to their selected position. The system can be checked. Put the flaps fully down with electrical and hydraulic power on, and then pod your button, and it will run through a self-test. Yeah. Extreme care must be taken working on or near the flaps. Yep. Flap drive systems, 2 separate means of operation. We've already talked through that. Could be a second hydraulic motor, could be an electric motor. Should the normal not be available, then the secondary, in this case the electric, is used to retract and extend the flaps. Spring-loaded centre off switch is provided to operate the electric drive. So when we've gone into the armed position, the bypass valve moves over, that isolates the prime source, and then using the spring-loaded toggle switch, we can ease the flaps down to the selected position. It's not like a normal flap selector. It's a little toggle switch, spring-loaded, and we just flick that up or down, and that will move the flaps to the next position. Some twin turboprop types use an electric actuator to lower and raise the flaps. Should the flap motor control system fail, the flaps can be operated manually using a cranking handle in this case. Yeah. Yeah, if it's not so much a cranking handle, but on the Jetstream, or our Jetstream, we've got a hand pump that we can operate, normally driven by an electric motor. If you get a failure in the electrics, we've got a hand pump we can use to put the flaps down in the event of an emergency. In this case, it's saying it's just a little rotating handle. Yeah, it's connected mechanically to the flaps. So we'll disconnect the electric motor. If we've lost power, open a panel and start winding the handle, and that will rotate the flaps down to where they need to be. Alternate position markings for the flaps are painted on top of the wings. Yeah, so by looking out of the window, we can see what position the flaps have achieved. Again, I can't speak for you guys, but our Jetstream's got that on as well. A little indicator, painted markings telling us where the position of the flaps is. Cable brake detectors, yeah, we've already talked about those. Just 2 little pulleys on the cables. If we get a break in the cables, spring will pull the pulleys together and make a contact in a micro switch, and that'll put a warning light on in the cabin. That was our trailing edge flaps. Has anybody got any questions on trailing edge flaps at all? No? Lovely.
Can
Yeah.
we have a 10-minute break? 10-minute break, please.
Yes, if you want, yes. Okay. I make that 11:40, so 11:50, just 10 minutes.
Okay, sir. Thank you, sir. Thank you.
Okay, cheers. 10 minutes.
Mr. Jim,
Yeah.
we have only 2 questions from fly-by-wire.
Is that according to the list, is it?
Yes, according to the list.
Okay, well, I've covered everything in fly-by-wire, and we've highlighted the important bits that I know about. The control laws, the architecture, and the other bits that we mentioned. So hopefully we've got all of that. I don't think there's a lot in flaps and slats. Yeah, but again, everything that I've recognised, we've said, run a highlighter through.
Mr. Jim,
Yeah.
question will come from only from the highlighted parts or some other things also.
No, it could come from anywhere, but all I'm doing when I'm saying stick a highlighter through that, those are bits that I've sort of recognised, or they jump off the page and say, look at me, I could be a question.
So it's better if you give us a question from that highlighted part, then it's easy for us.
Yeah, but I'm not here to make it easy. I'm here to try and help. Yeah, that's why I don't have to say highlight this, highlight that, highlight that. What I'm trying to do is give you the most likely places that the questions will come from. And the open questions that I'm sending out, if you think about it, yeah, those open questions are leading you to the areas where questions can come from. Yeah. I can't say where the questions are going to come from. All I'm doing is giving you my best shot at it, my best guess.
Maybe you are the one who are going to make the question for us. That's why it's better to help.
I don't get involved in questions.
Yeah, we are hoping we will get a lot of help from you. That's why we are expecting a lot from you, and we gain a lot of information from you also. And as that, we want some information as a exam point of view also.
Yeah, like I've said before, with the questions, we're not allowed.
Yes, you are not.
We can't give you multi-choice questions, but the questions I'm sending you,
yes, sir.
You know, they're going to give you the best chance of an answer.
Yes, sir.
Yeah. So
we expect all the questions will come from your highlighted parts. We hope so.
Yeah, but the bulk of them probably will. But I can't guarantee that somebody's not written a question from somewhere else. That would just be stupid of me. But just going off my experience, the areas that we've discussed are the most likely.
Okay.
But the questions I've been sending you, I've got a big batch for Module 11 that I'll send out at some point. But, you know, my question might say, what would happen if an aircraft was climbing and rolling to the left? What would happen to the elevons? And you'd write down the answer, you know, one side would remain up and the others would lower slightly. That answer could form part of 3 answers for a multi-choice question. So by answering the ones that I'm sending out, you know, you're getting pointed in the right direction. Do you see what I mean?
Yes, sir.
Because
we are going to work in the aircraft as per the manual. We need to just pass through this module.
Yeah, but like I said the other day, if you haven't got the understanding of you know, anybody can give you the answers, but what we're trying to do, as well as help you with the exam, we're trying to give you that knowledge that you need to be a good aircraft engineer.
Yes, sir. Yes, sir.
You know, if we don't do that, then it defeats the whole object of the exercise.
Yes, sir.
We're trying to get Nepali aviation up to a more acceptable standard. And as I said the other day, you guys are achieving that, but you're only going to do it through hard work.
Yes, sir.
There's no easy ways of doing it, and certainly me as a person and us as a company, we're not prepared to take shortcuts. We're here to produce good, safe engineers, not just somebody that knows how to cheat at an exam. There are companies that will do that, but we're not one of them.
Okay, sir. Hope we'll get easy question from you.
Yeah. So long as you put the reading in, it's not going to be a problem. And you know, I've got every confidence in you guys. And if you think about the exams you've done so far, you've done very well in them.
Okay.
Yeah. The pass rate for you guys on a whole is very, very good. So it shows you put in the work in, shows you put in the effort in, shows you put in the thought in. And Module 11 is going to be no different, just because it's slightly bigger. But again, you know, if you don't know the answer, you can draw on your experience.
Yeah.
Yeah. So
okay,
you know,
thank you.
That's the beauty of it. So right, just to finish off our flying controls, then we're going to look at leading edge devices. Your leading edge devices, your leading edge flaps or slats. Yeah, the first bit it starts off with is the leading edge flaps. Leading edge flaps have two positions. They are either up or they're down, fully up or fully down. Kruger flaps and variable camber flaps on the lower skin of the aircraft form part of the lower surface of the wing. Again, are a type of leading edge flap. Yeah, they'll either be fully extended or fully retracted. Yeah, your slats, they're different. Slats have slots, as again we saw the other day. Leading edge flaps, primary power to them provided by air motors. Yeah, it could be electric motors, it could be hydraulic actuators. Example is given, it says the primary power to position your leading edge flaps coming from a pneumatic system in this case, electric motors for your alternate means. Normal operation of the leading edge flaps controlled automatically by the operation of the trailing edge flaps. So if I select flaps down, the trailing edge flaps will move, and the leading edge flaps will move as well. Electrical signals, transmitted to the power drive units in each wing. Example described, the flaps are put into two groups. Group A flaps on each wing extend when the trailing edge flaps moved to one position, and then the rest of the group extend when the flap levers move to another position. So that these groups, depending on the position of the trailing edge flaps, the groups will extend at different points depending on the position of the trailing edge flaps. Again, that's an example system. Variable camber flaps provide more lift by being curved as they extend. Made from a composite, area of each flap increased by the folding nose, just improving the whole camber of the wing surface. Kruger flaps, similar, folding nose and form part of the leading edge. Yeah, your drive unit, as we said, we're going to have a drive unit. We're going to have the shafts, torque shafts, and again, the flaps will be driven down by actuators. Again, just from the notes, and there's a lot of pictures in the notes of examples, just showing the drive unit, showing the torque shaft, showing the actuator that's going to drive the things down. Nice picture of your Kruger flaps. You can see the bent nose. You can see that they form part of the lower surface of the wing when they're retracted. When they're extended, they'll improve the camber of the wing, and they've got the folded leading edge on them. Drive shaft, yeah, little rotary actuator that's going to swivel round and attach to the Kruger flap. Yeah, again, drive it down. Not a lot else to say there. The drive units provide the power necessary to drive the leading edge flaps. Power from a pneumatic system. Each drive unit contains a pneumatic and an electric power source. Allows both to use the same drive shaft. Very, very similar to our trailing edge flaps, yeah? So we've got two power sources, yeah, that can operate the flaps, but they'll go through the drive unit. If one's failed, the other will disconnect and allow the secondary circuit to run the control. Right, now then. Yeah, your Kruger flaps that is on the presentation. Yeah, you can see the actuator screw drive. Yeah, as it extends, it's pushing the Kruger flap via a carriage down to its fully extended position. Once we select flaps up, yeah, the screw jack will start to retract, and again via the track, the Kruger will retract. It'll move. The nose will start folding. And then once it's in its fully up position, it's tucked away inside the skin of the leading edge. Yeah, the variable camber, same sort of thing, but the positioning of the nose as the flap extends, there's more of a curvature on the nose of the variable camber flap. All right, it goes on in the notes to describe the operation of a pneumatic flap drive system. I honestly don't think there are that many aircraft now that use them, the pneumatic flaps. I don't really want to get bogged down in the ins and outs of how the thing works either, because we don't need to know. Yeah. But basically, try to look. Don't worry too much about this. Yeah, we've got a primary drive and an alternate drive, yeah, for our flaps. What's happening? We've got an air supply coming in. As we turn on the normal supply, yeah, normal supply will flow through and press down on a diaphragm. It'll open the air supply. The air supply is going to turn the motor. The motor will run in two directions, so it'll select up and it'll select down. The operation of the primary controller, your screw jack, we've got limit switches in the screw jack, and we've got a brake on it, so it's not going to shift when it's not selected. There is a means by which we can switch to an alternate supply, and by switching to an alternate supply, we can isolate the prime supply. It's long, it's complicated. I'll go into it if you want me to, but we don't need to. We don't need to know the internal workings of the pneumatic system. Yeah, there's no point in clogging our brains up with unnecessary stuff in this case. We can extend the flaps, retract the flaps.
Jim,
Yeah.
if it is not coming in exam, then no problem.
No, it won't be. The internal workings won't be, and I'm just looking through the text now, just to make sure that there's no sneaky possibilities in there. Yeah. all we're saying is it's a pneumatic system. We turn it on. Pneumatic system will drive the pneumatic motor. That pneumatic motor will run in two directions to either extend or retract the flaps. Yeah, and the extent of the motor running is driven by a controller here, and there's limit switches on it, which will trip the thing on, trip it off. Yeah. Just bear with me while I just make sure that there's nothing that was going to jump out and surprise us. Ching, ching, ching.
Excuse me, Jim.
Yeah.
Is it possible to put flap and slat in one aircraft?
Not normally, no.
Okay.
No, but it's because they work on different principles.
Okay.
Right, I can't see anything there that we need to worry about. Alternate operation leading edge flaps by means of the electric drive motor. Yeah. Arming the switches. You've got to arm the flap switches first before you can move them. When we select the emergency, that shuts off the air to the normal side, isolates it so the electric motor can drive the leading edge flaps. Yeah, can't see anything on there that we need to fret about. So I'm not going to. Yeah, suffice to say that we open up a pneumatic supply. The pneumatic supply drives the motor. It can drive it in one direction or the other. If we get a failure in the system, then we can open it up to an alternate control. Yeah, your emergency motor there, and that's driving your flaps. Yeah, so if we get a failure in the pneumatic side, we can isolate the prime, the pneumatic side, and the alternative running off an electric motor via some gears there is going to do the job for us. Your alternate flaps, they're just an example of your emergency switch. Yeah, so you can select them up, you can select them down, you can have the thing off. Yeah, so we can, with our switch, we can put the switch into the armed position. Yeah, and then flicking the lever up or down will move the flaps to the required position. Exactly the same with the leading edge flaps. Yeah, a guarded switch. Take the guard down, select it to the armed position, and then we can flick the toggle switch, and that will move the leading edge flaps again to the required position. Yeah, the placard that we talked about before. Yeah, it's going to be there to show us what the limits are for the positions of the flaps for the various airspeeds. Yeah, so if I'm flying at 280 knots, I can select position 1. If I'm anything above that, we've got the auto retract. Yeah, the alternate selector. Yeah, again we've got the armed switch. Yeah, so we're going to armed. And we can retract or we can extend the flaps as we see fit. Nothing else there that we need to worry about, I don't think. Leading edge flap position indicator, yeah, provides the pilot with visual indication of the operation of the flaps, normal and alternate operation. Yeah, amber leading edge flaps in transit. Green lights mean that they're extended. Hopefully we've got a picture of that. Sure it comes up later. Leading edge slats, yeah. Slats, we've got 3 positions on the slats, don't forget. So we can have them fully extended for landing. We can have them in the intermediate position for takeoff and fully retracted for in the cruise when we're up to speed. This one shows a cable-driven system. Yeah. Again, we've got our lockout mechanism included there for the ailerons. So once the flaps are retracted, the aileron lockout can go in. Yeah. Leading edge slats, they're going to drop down and provide a slot for us. This particular one, each slat's supported by 3 tracks that ride along rollers. Center track on each slat is the drive track connected to the operating system. The other tracks are idler tracks. Stops fitted in the idler tracks to prevent slat over travel when they're extending and retracting. As we said, page 220. Yeah, the second, or is it third paragraph, the slats have 3 positions: retract, take off, and fully extended. Yeah. Flap slat control handles operated. The slat control cable system operates a hydraulic selector that directs hydraulic fluid to the actuators. They rotate and the slat drive drums, and that drives the slats to their selected position. Nothing else we need worry about there. So that the cables attached to your drive mechanism. Your drive mechanism running your actuator. Yeah. So you got your actuator. You've got the main tracks that the slat's going to run down, and you've got the auxiliary tracks. I think we come on to it, but I'm pretty sure the auxiliary tracks stop the slat from twisting when it's travelling. It keeps it going in a straight direction. Bear with me on that one. I'll just have a look in a moment. Yeah, slats operated by the flap selector lever, retracted when the lever's at 0. Take off when we move to position 1, and fully extended when we go to the flap landing positions. Reversed on retraction. Auto slat normally installed that automatically extends the slats to prevent the wing from stalling at low speed. That auto slat we'll look at in just a minute. Leading edge slat mechanism positions the slats as required. The slat is guided by 2 main tracks. Yeah, and then a hydraulic actuator, 3-position actuator attached to the center of each slat. Auxiliary tracks mounted on the front wing spar stabilize the slats at the intermediate position. Sometimes called a programming track, but they're there to make sure that the slats are stable in the intermediate position when takeoff selected. The main tracks act as guides and contain the stops, the travel limit stops. So your main tracks, yeah, nothing there to worry about. And the main tracks, you've got your stop bolts, so that'll physically stop the thing from travelling when we're in the fully up and for the fully down. The auxiliary tracks, the little green ones, are there when we're in the intermediate position. It says to stabilise the thing. It just means it's not going to twist. It's going to stay nice and rigid and square on the airflow. Yeah, retracted. There's your track that the slat's going to run down. The intermediate position, just a little day tent. Yeah, we'll get to the intermediate position, we'll hold there, and then when we select fully down, we'll come out of the day tent, and as we reach the bottom, we'll form a slot. Nothing else there that we need to worry about. Showing you your rollers, the down stops. Down stops fully extended, yeah, mating up with the down stop on the structure. You're not going to go any further. Your rollers allowing it to roll, and then when you come back up, again we're away. Actuator, yeah, and again the actuator is allowed to pivot to account for the motion and the movement of the slat. Yeah. So as it extends, it will pivot down on its bearing at the high end. Yeah, flaps. Yeah, it's a takeoff range, landing range. The slat drive, the trailing edge flap drive. Yeah, taking a feed from the flap lever. Yeah, and the flaps selected. Talking to the slats, hydraulic motor, yeah, and the bypass valve in there. Should we get a failure, we can isolate that hydraulic supply and use an alternative supply to drive our slats. Indication, yeah. Actuator just talks about the actuator. How the actuator is working. Nothing we need to know there that we haven't already covered. Yeah. Switch inside the slack actuator sends a retract or not retracted signal to the indicating system. Proximity sensors mounted on the leading edge structure. So amber and green lights for each leading edge device on a panel in the CWP. Master lights, one amber, one green, located on the pilot CWP. Amber lights when the devices are in transit. Green lights when they're in the extended or retracted position. Yeah, and that's the sort of thing we're looking at. Yeah, the slat lights. Yeah, slats in transit. Slats locked at the intermediate or takeoff position, slats at the fully extended or the landing position. Yeah, press to test for your lights, and away we go. So that's a typical example of the indications that we might get. Again, taken from the aircraft, yeah, showing them in transit, yeah, and your intermediate and your fully extended positions. Flap positions, yeah, depending on where your flaps are, all the slats in the extended position, flaps fully extended, flap positions 10 through 40, all the slats in the full extended position. So just there to remind the pilot, and that's off your 737. Again, nothing I don't think we've not spoken about. Drive unit, power drive unit used to extend or retract the slats. Normal operation hydraulic, alternate electric. PDU drives the torque tubes. They run down both leading edges, same as our trailing edge flap system. And the torque tubes drive the actuators which operate the slats. Yeah, so that's if you've got the torque shaft system as opposed to the hydraulic actuators. Again, at the end of the transmission shaft, you've got position transmitter, and again, that's going to be feeding back information to the gauge in the cabin. Again, not a lot else to say on that one. Yeah, rotary actuator, rack and pinion type thing with a gearing that's going to operate the slats. Yeah, using a rack and pinion, and we know what that is. Yeah, so again, just a different method of transmitting to the things. Right, page 231. Yeah, the auto slat system. You just need to be aware of this. Yeah, the auto slats are there to prevent the aircraft from, or help prevent the aircraft from stalling. 2 stall management computers normally installed to operate the auto slats. Each stall management computer combines the function of auto slat operation and stall warning. The stall warning computer is mounted in the electronic equipment compartment. Yeah. And there's a press to test facility should we need it. Auto slat operation is inhibited when the aircraft is weight on wheels. Yeah, the auto slat control valve provides the means of extending the slats when we reach a high angle of attack. The stall warning computers will be monitoring that, and when we get to a certain point, yeah, the stall warning computers will send a signal to the auto slat control valve. And then the auto slat control valve will extend the slats. Once we've come out of that stall condition, yeah, regained a safe speed, the stall computer will retract the slats for us. Yeah. So the idea is if we're flying too slowly, too high an angle of attack, whichever, as we're approaching the stall angle, the auto slat system, part of the stall management system, will automatically deploy the slats. Yeah, that will give us more lift over the wing and give us time to recover the aircraft. Bring the nose of the aircraft down, bring the speed back up, and then the slats will automatically retract. Again, there's a built-in test for it. Yeah, auto slat failure warning comes from the stall management computers. Yeah, and you'll get a warning light in the cabin. We can have a slat loss or an asymmetry sensing system, may be incorporated as it says. Yeah, and what happens, the slats have a cable running laterally inside the curved section of the slat. Cable attached to a micro switch mounted in the leading edge. If the slat separates from the aircraft for whatever reason, yeah, that cable will pull on the micro switch and activate the micro switch. That'll send a signal which will say, oh, you've got an asymmetry, and the slat system will shut down. Yeah, the asymmetry detection system, we can put one of those in and it'll operate the same way as the trailing edge flap one that we've said. Yeah, it will be monitoring the torque shafts, transducers at the end. If there's a disparity in the signals that are being sent to the comparator, it will shut the system down. Yeah, it'll lock it up, and again, just like the trailing edge flaps, it won't allow us to reset till we're on the ground. Again, your asymmetries can operate independently, so you might lose your slats, but you want your trailing edge flaps to carry on operating. Yeah, you might lose your trailing edge flaps, but that won't stop the slats operating. Again, in all my experience of aircraft, yeah, they've operated independently. So your slat loss, yeah, or your asymmetry detection, again, locking the system up. Page 233, configuration warning. Yeah, well worth remembering the contents of this. Before the aircraft can take off, the crew have got to go through a checklist procedure to make sure everything is safe. Yeah. To make sure that nothing goes awry because the crew are distracted or whatever, we have a configuration warning system in the aircraft. So if a takeoff is attempted with the aircraft in the wrong configuration, the system will give us a visual warning lights, whoop whoop, and the audible warning as well. Yeah, the system is looking for throttle positions. Yeah, so the circuit initiated by any throttle lever being advanced to the takeoff range. Yeah, and the system monitoring what's going on wants to make sure that we're on the ground. Yeah, because the configuration is going to change as we get airborne. So it's looking at the position of the wow switches. It's looking at throttle positions. So as the throttle moves forward, yeah, it's looking to see where the speed brakes are. So the speed brakes should be in the fully down position. Yeah, it's looking at the nose wheel steering and the body steering for the bogies. Yeah, making sure that it's centered so it's not going to drift off track. We're looking at the position of the trailing edge flaps to make sure that they're within the takeoff range, and likewise it's looking at the position of the leading edge flaps or the slats which are ever fitted to make sure that they are in the correct position for takeoff. This one's showing the leading edge flaps down, but if it was slats, it'd be in the intermediate position. The other thing it monitors for that we mentioned is the green band on the stabilizer position. Yeah, so it's looking to make sure that the stabilizer is in its correct position for the takeoff. Yeah, if any of those are out of line, not in the correct position, we're going to get a warning light and a warning horn sounding in the cabin. Yeah. So that's your configuration selection. And that brings us to the end whistle-stop tour of flying controls. Has anybody got any questions on any of that? No? Deathly silence. In that case, we'll break there for lunch. I make it 12:30. Kathmandu time. Where's Kathmandu? Kathmandu 18:15. So 19:15 for you guys. 1 hour for lunch. Okay.
Okay, sir.
Yes, sir. Thank you.
Okay. I'll see you in a little while.
Okay, sir. Have a nice night.
Thank you.
Jim,
Hello.
you are busy?
No.
So I was going through this pitch control system in fly-by-wire.
Yeah.
So like in the event of total loss of electricity power,
Yeah.
the elevator servo will remain stationary and provide damping.
Yeah.
Or the servo move to neutral and lock?
It's hydraulic pressure at either end of the servo. Yeah. So when it goes, pardon me, when it goes to neutral.
Yes.
Yeah. Hydraulic pressure is ducted to either end of the servo, and it stays in a neutral position.
So there must be damping also.
Yeah. I suppose it depends on the type of actuator, but the example actuator that we looked at, it's got the interconnecting valve in it. Yeah. So when you lose hydraulic pressure, that interconnecting valve closes, well, opens the two chambers to each other. Hang on, just let me. Can you see the presentation slide?
No. All right. Yes.
Can you see that? See that now? The actuator we were looking at, we had the pressure in. Yeah, I'm trying to draw this from memory. And then you had the line going to down to the servo, one side of the servo or the other. Yeah, your servo housing's down here. And then down here you had the interconnecting valve. Yeah, and the interconnecting valve lived on a spring. Yeah. So when you've got hydraulic pressure coming in, yeah, that pressure is acting on that piston and allowing the oil to go off to either side. Yeah. That's something like that, wasn't it? That was right, and that went into the servo housing, and your servo was in here to block off the two ports. Yeah, something like that. But when we lose hydraulic pressure, yeah, that hydraulic pressure vanishes. There's nothing holding that interconnecting block down now. So what happens is the
spring will move it up.
The spring pushes it up. Yeah. So now the two halves of the actuator are opened up to each other. So if again, badly drawn because I haven't got the slide up. I'll try and dig it out in a when we have tea break later. I've lost my little dot now. Where's my dot gone?
No problem, Jim. Yeah.
Yeah, but what happens is, come on. Either side of the actuator, yeah, as the actuator's moving, oil's just being passed from one side to the other, so it goes into damping mode. You with me?
Yes.
Yeah. So. Yeah, so that's how one would be in damping mode. Well, obviously, depending on the complexity of the actuator, it depends how they're gonna do it.
You will be giving some fly-by-wire questions today.
The fly-by-wire questions I think went out on the sheet I sent yesterday.
Okay, all right.
Okay with that then? Has that answered your question? Okay. Right, what we're going to do this afternoon then, unless anybody else has got any questions, we're going to kick on with landing gear. Quite a big book, but there's a lot of pictures in it, so the actual content we can thin down. So we'll go through the various bits, pump in quite a bit this afternoon, and then finish it off tomorrow. Because I think I finish with the B2 guys tomorrow, don't we? Yeah. Right, so landing gear then. Yeah. Obviously, when aviation first started, all that people wanted to do was to get up in the air, to fly, conquer the skies. But what they didn't think about was getting back down to earth again. So there were a lot of fatalities and injuries in the early days of aviation, mainly because they didn't have a reasonable method of getting back down onto the ground. So over time, they started developing landing gear, and obviously, from the primitive landing gear to the stuff we've got now, it's all fulfilling the same function. Yeah, it's got certain criteria to meet. Even up to, you know, from that little light thing just there to carrying tons and tons of weight. The whole purpose of the aircraft is to get the thing back down onto the ground in a safe manner. Yeah. But the primary functions of the aircraft, and again, these are blocked in the notes, so just make a note of them when you're reading through. Yeah, the primary function of the landing gear is to support the aircraft in a stable attitude. Yeah, support the aircraft on the ground, but to support in a stable attitude. Other functions it's got to provide is to provide mobility on the ground, so we can get around the airfield. It's got to absorb landing loads. Not only the shock of the direct vertical descent, but we've got forward motion as well. So we've got to absorb those landing loads, dampen out any noise and vibration, making the ride comfortable while we're taxiing. Give us a means of steering on the ground, and give us a means of braking as well. Yeah, so those are the sort of prime functions, the primary function to support the aircraft on the ground. The other functions giving us that additional functioning. That doesn't run. Just a minute. Somebody's binging and binging and binging. No more binging. Yeah, so there are different types of undercarriage layout. But it says the main type of gear for large aircraft over 5,700 kg, we term that the tricycle undercarriage. Yeah, it comprises of two main undercarriage, one nose undercarriage units, but there are variations of that. So your tricycle undercarriage, the standard, the nose gear, and the main gear fall in the tricycle shape. But variations, the wing body setup, and the centerline setup, but we've still got that tricycle. We're just putting additional bits of gear in there into the system. Yeah. Again, the notes, lots of nice pictures, just showing you the variations there. The advantages of the tricycle undercarriage are pretty good, yeah. The far outweigh the disadvantages. The advantages, pretty much the pilot has got a virtually unobstructed view. He can see for miles around him. Yeah, that layout gives good forward stability to the aeroplane, and that forward stability allows efficient braking. main disadvantage is the fact that the center of gravity may move. Yeah, if fuel shifts or cargo shifts, we can overcome the C of G. The weight moves behind the C of G, and the aircraft will sit on its backside. So that is a big disadvantage. Yeah, the C of G shift. And remember that the center of gravity shift is the main disadvantage of the tricycle undercarriage. Yeah. So what we're going to do, we'll design the aircraft so that the gear is always going to be as close to the C of G, or the layout of the gear as best we can get it. Nice example of the fact that they were unloading this aircraft. Again, didn't unload it properly, and that was the result. And it still happens. Still happens even today. Is it Korean aircraft that comes into Kathmandu once a day, isn't it? Big thing, big huge aeroplane. Or it did do when I was out there. Very similar colours. Yeah, so we want to make sure that the center of gravity position, that the undercarriage is arranged around there. Yeah, and we need to make sure that the undercarriage units are mounted on strong points of the aircraft structure. Yeah, so you know, the size of the aeroplane, the weight that they carry now, lots and lots of weight. So we need to make sure that the structure is going to be strong enough to support that. Without allowing any damage to the aircraft structure. So generally, the main landing loads are taken on the main undercarriage, the nose undercarriage only taking a small portion of the load. But the nose undercarriage, very important because it allows us to steer the aeroplane, get from A to B, and supports the front section of the aeroplane. Fuselage section of the aircraft, strong points may be located next to a frame or the juncture of a frame or a stringer. And the wing spar section of the aircraft, the ideal strong points adjacent to the main spar. So all we're saying is wherever we're putting the undercarriage, yeah, we've got to take the C of G into consideration, and we're going to put it next to big strong points on the aircraft structure, so it can take the loads associated. Moving cargo, moving fuel. This was a brand new aeroplane. It was on its delivery flight from the manufacturer to a company, and it came with ballast weights fitted. Yeah. What the guys did, they were meant to replace the ballast, putting radar equipment in and various avionics stuff. But rather than getting everything in place before they'd removed the ballast, they just took the ballast out, and of course everything went to hell in a handcart, and it sat on its backside. And for a brand new, not even been painted, it's still in its primer, spanking brand new aeroplane. Not very nice for the company. Yeah. Like we say, the location of the landing gear from the sublime to the ridiculous has got to correspond with the strong points on the airframe. So big frames, obviously, and the landing gear mounted adjacent to those frames. So as the gear hits the ground, the landing loads and the shock loads are going to be transmitted up into the fuselage and dissipated through the fuselage. It's quite a nice aeroplane, that one, huh? Ta-da! So that's our gear location. Yeah. Again, straight from the notes, yeah, sort of things we're looking at. We've got a main. In this case, I think it's the wing spar. Yeah, and the mounting point for the main landing gear actuator, the mounting point for the main landing gear, mounted in those strong points. Yeah, and then we've got the peripheral stuff, the retraction actuator, the downlock actuator, drag brace, and all the rest of it. But we're attaching the undercarriage to strong points on the fuselage. Yeah, those landing gear attachments designed to transmit the landing loads through the aircraft structure, and the main method of attachment, I'll come on to it in a second, is called a trunnion. Yeah. Wrong button. Yeah, the trunnion, big bearing housing, and there's a pin on the undercarriage leg, fits into the trunnion. So if you can imagine, just a second, do that in red so I don't lose my little dot. That's the top of the undercarriage leg, yeah, and then it goes off to do its undercarriaging thing. Yeah, this trunnion, as they call it here, is going to fit into a bearing housing in the main structure. By allowing that to fit into the housing, the trunnion has now got somewhere to swivel. So we can retract the undercarriage, we can swivel it up and down, and it'll swivel around that trunnion. When the aircraft lands and you get all the landing loads, yeah, that trunnion is mounted in structure. It's strong enough to absorb those loads. Yeah, so that's your trunnion. Trunnion, that's a pivot point supported by bearings incorporated in the aircraft structure. What else do we have in there? Yeah, the structural fuse. I'll show you that on the next slide. But the structural fuse down at the bottom of page, wherever I am, 15. Yeah, stick your highlighter through that bottom paragraph. The whole purpose of the structural fuse is to fail under excessive load. Yeah, so it's protecting the primary structure. Yeah, so designed to fail under excessive load before damage to the primary structure can be caused. Yeah, if we didn't have that, there's a good chance.
At what page number you told to highlight?
15.
15, last paragraph.
Thank you.
Yeah, if we didn't put those structural fuses in, there's a good chance that if we had a heavy landing, that the undercarriage leg could go straight up into a fuel tank, rupture the tank, and all the shit, death, and disaster that entails. So we fit the structural fuses in. Looking at the slide, that is your trunnion at the top of the undercarriage leg. Yeah, and the trunnion via a bearing goes into the aircraft structure. That's your trunnion bearing. Placed in there is this structural fuse. Yeah, and the structural fuse designed to fail to protect the primary structure. Please remember that one. Not guaranteeing it come up, but it does quite often. Everything held in place quite nicely. Padme, so you've got the layout of the leg. This one, the leg's going to retract up into the root of the wing and the fuselage. Yeah, so we've got the downlock strut. That's opened and closed by a little actuator. Yeah, the main shock strut held in place by the trunnion in strong points on the wing rib. Yeah, and within there, it doesn't show it on here, but within there, we're going to have our structural fuse. So if anything did happen, heavy landing, rather than allowing the leg to go straight up through a fuel tank, the leg would collapse and the aircraft would skate along on its engine housing. Yeah. All okay with that? Yeah, structural fuses, trunnions. Yeah, making sure that we've got our basic undercarriage shape there then. Don't forget the tricycle undercarriage, although we do have little variations, but the layout of the undercarriage deems it to be tricycle, certainly on aircraft over 5,700 kg. Slower, older aircraft yeah, are fitted with fixed undercarriage. Yeah, it doesn't retract during flight. That'll create a bit of drag, but does it matter? Because the aircraft's that slow anyway, it doesn't really affect the performance of the aeroplane. And the advantages of the fixed undercarriage for your smaller aircraft, much simpler. We haven't got the costs involved. We haven't got the maintenance to be carried out. So it's a good arrangement for smaller, lighter aircraft, the fixed undercarriage. It's going to absorb the landing loads, as we'll see in a minute, because of the leg is mounted to a frame on the fuselage at a strong point, and the leg struts are flexible. So as the aircraft hits the ground, the struts will flex and absorb those loads. To get around the drag, we can fit fairings over the wheels, and those fairings are known as spats. Yeah. So again, on page 18, yeah, the fairings that are fitted over the exposed wheels known as spats. Yeah. And they are there purely to reduce the aerodynamic drag that might build up on the aircraft. Retractable undercarriage is going to allow the aircraft to fly a lot faster. So the faster types of aircraft, we don't want all that drag. We need to make the aircraft more aerodynamic. So what we can do is pull the undercarriage up into the body of the aeroplane, and that'll give us a nice smooth aerodynamic profile and reduce all the drag that would be generated. Yeah. So most modern aircraft, the landing gear is retracted into the structure of the aeroplane. Nice, smooth, streamlined shape that we've talked about. But there are a couple of disadvantages to the retractable undercarriage. It's got more components, therefore we're going to increase the weight of the aeroplane. To get the gear up, yeah, got to stow it somewhere, so it makes design a bit more complex. And obviously, with all those moving parts, we're going to have extra maintenance to be carried out. Just while it's on my mind, and I can't remember whether we'll come across it later, when we're talking about fixed undercarriage and we're talking about tricycle undercarriage, yeah, we don't necessarily have to have the nose wheel at the front. It's an accepted convention. But some aircraft, we have a wheel at the back of the fuselage, and those aircraft are referred to as tail draggers. Yeah. They have a much more restricted view from the cockpit, and when the pilot's taxiing, he's got to weave the aircraft backwards and forwards so he can see. Yeah, so I'm not sure whether it comes now or later, but tail draggers, just remember them. Yeah, so your retractable gear brought up into the belly of the aircraft and stored, so we get that nice aerodynamic profile. That landing gear, yeah, is subject to an awful lot of abuse during the lifetime of the aircraft. Yeah, very rough treatment, where it's operating, the different environments it's operating in, working in rain, in slush, snow, desert, all the different conditions we expect that undercarriage to operate in. Maybe that we take off from, I don't know, Kathmandu in a monsoon, and you've got all that water on the runway that's splashing up into the undercarriage units, and then we get to Dubai, land at Dubai, and we've got all that sand, and of course the water, because it's been at altitude, is going to thaw when the aircraft descends, so you've got the sand sticking to it. So to make sure that the undercarriage is fit for purpose, fit to do its job, we need to carry out regular maintenance. Yeah, and that maintenance, generally it means cleaning the thing. Yeah, get rid of all the oil and dirt and crap that's accumulated on it. And then we need to inspect it, because of the loads it takes. They are very prone to damage. Yeah, even though they're very, very good and robust design, they do end up damaged quite often. So good maintenance, good inspection regime to make sure that the thing is kept in the best possible condition. It's always good. Yeah, we can see all the dirt that's accumulating. Yeah, so we need to keep it nice and clean. This one, you can actually see this video on YouTube, I think it is. The guy was flying around, one of his landing gears stuck up, and what they did is his mates in a car ran down the runway as he flew above them. He was going as slow as he could, he was going as fast as he could, and they managed to reach up and pull the undercarriage down. Lucky, they were successful. They were lucky to do it, though. But if you want to laugh, have a look on YouTube for it. Yeah, and buried beneath all the dirt and the grime, this is the sort of thing that we can find. Yeah, the aircraft had a heavy landing. Yeah, the undercarriage unit's cracked. But if that was hidden by layers and layers of dirt, you can see the black dirt there. If it was hidden by those layers of dirt, you might well miss something like that. So again, cleaning everything off on the undercarriage and giving it a thorough inspection is vital to its well-being and its continued serviceability. Yeah. Ta-da! Everybody okay with that? Right, aircraft wheels then. Yeah, the wheels themselves. Yeah, your wheels on the aircraft, it says that they include the brake units. Yeah, the wheels in the brake units are often classed as one, even though they are separate entities. They're normally, because they're working together, we tend to lump them together. So that the wheels and the brake units and the tyres that are there, subject to extreme conditions during normal operations. Yeah, those extreme conditions include very, very high temperatures. Even though those high temperatures are quite normal for the operations that we're doing. Excuse me 1 second. Pardon me, thank you. Yeah, so we're going to get very high temperatures transmitted through the wheel from the brake unit. Yeah, heat's created by the conversion of kinetic energy and the aircraft's forward speed to the heat energy in the braking process. Right, when we come to do brakes, that line is repeated, but just so we don't forget it, yeah, that first bullet point on page whatever we're on, page 21, yeah, heat from the braking is due to the conversion of kinetic energy of the aircraft's forward speed, forward motion, into heat energy, because we're applying the brakes, and that's how the brakes work. We will put that down later on. We do come across it again, but make sure you've got that in your head. the aircraft's going to be subject to some really heavy loads as the aircraft's landing. And those landing loads transmitted down through the aircraft structure, through the shock absorbers, the wheels and the tyres. Yeah, and the whole weight of the aircraft is put down on the undercarriage, on the aircraft wheels. The other thing that we're going to suffer from is the climatic conditions, yeah, in flight and on the ground, and we're going to have a potential for real variations in temperature. Sitting on the ground in Dubai, really hot. Take off, fly up to altitude, really cold, and then land in, I don't know, Kathmandu, really nice. Yeah, so the climate is going to change, and obviously Kathmandu in the valley, you've come across the mountains, all the rest of it. So it's got all those climatic conditions and the temperature ranges, the moisture that's in the air. The dirt and the dust that we've already mentioned. Yeah. So the wheels are going to suffer quite a lot. Yeah. So when we're servicing the wheel and inspecting the wheel, we've got to look out and take these things into consideration. Yeah. Again, you know, the whole weight of the aircraft now being taken on one undercarriage unit, as you can see on the slide. The undercarriage is designed to be able to do that, but you can imagine there's an awful lot of stress goes through there. If we're landing and we have heavy braking, there's possibility of the tyres bursting, extreme heat from the brake units. If we've got oil leaks from hydraulic systems or anything, that extreme heat can ignite the wheels and again fire damage. Yeah, so friction generated through the landing and the braking loads can be quite iffy for the undercarriage. Yeah, and again, just thermal camera, just showing the different heat distributions that we can develop and how that temperature varies. And again, you know, just the snow and the crap that's covering the aeroplane. Yeah, and the wheels are going to be the first interface to deal with that. If the aircraft has had a heavy landing, has suffered large variations in temperatures, what can happen is that the extreme temperatures will build up pressure in the tyre, and because of the additional pressure in the tyre, there's always a potential for the tyre to explode. Yeah. So due to the serious risk overheating and the risk of explosion, if your aircraft has had a heavy landing or has carried out heavy braking, yeah, we want to stay away from those wheels for as long as we possibly can. Yeah, so ideally the answer is to tow the aircraft off the runway and leave it till everything's cooled down. Sometimes that's not always possible. Yeah, and we might have to walk into the tyres. If we do, we always come in at 45 degrees or an oblique angle to the tyre. Yeah, coming from the shoulder area. If that tyre explodes, as you see with this one, the bolts that are holding the wheel together are under enormous pressure. And what can happen? The bolts can shear, or the rim can come off the wheel, and it'll come out of with all that pressure behind it. It'll come out like a bloody torpedo. Yeah, and if you're standing in the way, pretty much kiss everything goodbye. Likewise, if the tyre tread is weak, as we saw on that that slide there, if the tyre blows out from a patch like that where we've braked or we've skidded, you've got all that pressure coming straight out at you, and if the rubber shreds, again, that's like bullets coming at you. The strongest part of the tyre is on the shoulder, on the sidewall there. So if we come in at a oblique angle, we're in with a better chance of not being injured. But ideally, if you've had a rejected takeoff, heavy landing, heavy braking, tow the aircraft off the runway or taxi it off the runway and leave it till everything's cooled down. Yeah. And out of that little lot, yeah, the bottom sentence on page 21, when necessary, always approach a damaged, overheated tyre or wheel assembly from an oblique angle in the direction of the tyre shoulder. Stick your highlighter through that one, por favor. Right, has anybody got any questions on that little lot before we move on to the wheels themselves? No? Okay. Lovely. Wheels then. Wheels are usually made from aluminium alloy, either forged or cast. And then, sorry? No. We further protect the wheels then from corrosion by anodizing. Remember anodizing from the structures we did the other day? Yeah, it's a means of protecting the material, a chemical conversion where we use the aluminium alloy as the anode in an electrolyte bath. Yeah, some wheels then, quite a lot of them in fact, then get further protection by being painted. Yeah, it says e.g. Concorde. There are a lot of painted wheels on the circuit. Yeah, so aluminium alloy, anodize them, paint them. With our wheels though, because of the environment that they're operating in, if that protective finish gets damaged, it needs to be restored as soon as possible. It says there immediately, but obviously that's not going to be practical. But as soon as is practicable, we need to get the wheel protection restored. If you start getting corrosion in there, it's going to weaken the wheel structure, landing loads, fracture the wheels, big problems. Yeah. There are two types of wheel, two main types of wheel. There's the removable flange wheel and the split wheel. The removable flange is, as the name suggests, the flange is held in place by a big locking ring. When we dismantle the wheel, yeah, once we've let all the pressure out, again, we'll come on to that, quite critical. Let all the pressure out, we come to dismantle the wheel, we remove the locking ring, and that flange will come off the wheel. We can then remove the tyre, replace the tyre, put the tyre back on, and then replace and lock in place the flange. They exist, they are around, but they're not probably the most common. Yeah. Yeah, made with one flange integral with a hub, the other flange removable, retained by a locking collar, sealing by use of an O-ring, adjacent to the removable flange for use with tubeless tyres. Yeah, and again, we're just the various components that you get. The main thing for us to worry about is the flange. Yeah, means of inflation, putting an inflation valve in. Drive blocks, we'll cover those in a minute, allow us to engage with the brake unit, and the bearings, back-to-back bearings, allowing us to slide and rotate on the axle, main wheel axle. Probably the more common type of wheel is the split wheel. Yeah, the ones you'll come across most often. Yeah, made up of two equal mating halves, and those halves joined together by bolts passing through. Sealing by an O-ring fitted between the two halves, and we use these with tubeless tyres. Let's see what else we can point out here. Yeah, so we've got the two halves of the wheel, two half hubs, held together by bolts, and bolts and nuts, tie bolts as they're known. Again, we've got the bearings to allow us to rotate on the axle. Inflation valve, so we can get air into the thing. Drive blocks, so we can engage with the brake units, and heat shields fitted onto the inside of the wheel to deflect the heat that's being generated during braking. Yeah, on this one, and again we'll cover it again in a minute, we've got a fusible plug. And the idea of the fusible plug is if we have a heavy landing, heat build up in the wheel, or rejected takeoff or whatever, that heat builds up, yeah, and that's going to build the pressure up. If we don't do something about it, that pressure could carry on build until we get that explosion that we talked about. So by putting a fusible plug in that's designed to melt a particular temperature. And as it melts, it's going to let all the pressure out the wheel in a controlled manner. Yeah, so that's the idea behind our fusible plug. Nothing else I really need to mention there. The O-ring that fits between the two halves just to seal it. And the little holes you get in the hub, again, they're there to allow us to dissipate the heat that's generated through braking. So the heat generated by the friction created during braking transferred by, radiation and conduction through the wheel and into the tyre. So the wheels are designed to dissipate that heat. Main way is by that venting. Yeah, so we put those holes in, and that allows, as the wheel's rotating, it's allowing fresh air to blow through, and by blowing that fresh air through, we're blowing away the heat. Yeah, so the wheels are going to be vented. Heat shields, as I mentioned before, these little heat deflectors may be installed around the brake unit, again just to deflect heat away from the tyre. And on some larger aircraft, we actually get axle fans. So fans built into the axle, and they're going to, again, blow away the heat and provide cooling air through the wheel to the brake unit. Do you need to know that? Don't think so. Right. Right. On the wheels themselves, I was talking about the thermal fuses. Yeah. We may well have overpressure relief valves put into the wheel, built into the wheel. So again, if that pressure builds up, the relief valve is going to release it. Some aircraft have tyre pressure sensors, and the tyre pressure is relayed up to the flight deck, so the pilot can see what his tyre pressures are. And obviously, we need to get an inflation medium in there, so we're going to have an inflation valve. Yeah. Inflation valve is just your standard Schrader type, exactly the same as you get in your car or in your bike. Yeah, and they're either long core or short core. It doesn't really matter which. It's up to to the manufacturer which one you're going to put in. There's no real difference between them. The overpressure relief valve, as I say, may relieve pressure above a certain point. It quotes the Boeing 777 as having them, and they relieve at about 375 to 450 psi. Depends on the tire pressure. Tire pressure sensor I've already mentioned sends the pressure data to the indicator in the cabin, and then we've got our thermal plugs. The thermal plugs depends on the manufacturer, but they will melt at a particular temperature. Example of the colours in this one, we'll get a red one that melts at 155 degrees C, green one will melt at 177, and a yellow one at 199. That colour coding is decided by the manufacturer, so they're not standard. A red one from Dunlop, 155 degrees, a red one from Goodyear might be 199 degrees. So the only way that we can positively identify the correct thermal fuse is by part number. So although they are color coded, the only proper right way of identifying it is by part number. That's on page 28, and that is definitely worth sticking a highlighter through. All thermal fuse plugs must be identified by their individual part number, not by the color coding. All okay with that?
So Jim?
Yeah.
So it is heat shield which prevents some of the heat being transferred to the wheel assembly?
Yes.
Thank you.
Yeah. Right, our wheels then, the wheel mounting. Wheels are mounted on tapered roller bearings. And the tapered roller bearings fit directly onto the axle or onto a bearing sleeve, which is attached to the axle. To reduce the effect of the impact loads, the bearings, when the aircraft lands, the bearings are allowed to slowly move on the axle. And the reason for allowing the bearings to creep around the axle is to even out the wear. If we didn't allow that, you'd get the same point taking all the load constantly. A bit like was said in the fuel system. So with the cascade device, we're dissipating all the fuel that's going into the tank, so it's not striking one point. With the bearing, and some bearings we allow them just to move slightly on the axle, just to wear even the wear out. And it says that also simplifies the wheel removal and replacement. Some nose wheels, are mounted on a live axle, so that it's the axle itself that's rotating on the nose leg. So again, the way the wheels are mounted, kind of aircraft dependent, but they're all going to work through bearings. Again, as it says on the slide there, the bearings and the wheel mountings have got an awful lot of stress and strain to cope with. 500-ton aeroplane touching down on the runway, all that load is transmitted from the airframe through the wheels. So the wheel bearings, as they touch the ground, they've got to go from 0 to 2,000 RPM in next to no time, less than a second. And again, as they start braking and reverse thrust supplied, the wheel's slowing right down. There's going to be a lot of heat generated. So the mounting of the wheels and the shocks that are going to take is quite important. Your tapered roller bearing, remember that the wheels are mounted on taper roller bearings. And we've seen the bearings in Module 6 and Module 7. I don't think we need to worry too much about that. Your aircraft, we looked at the light aircraft earlier on. And the landing gear strut attaches to one of the main frames in the aircraft. And on the end of the landing gear strut, we've got the axle. On the axle, we're going to mount the wheel. Yeah, and the wheel will be locked on the axle and allowed to rotate via the bearings. Ding, ding, ding. Yeah. Obviously, maintenance on the wheels again is fairly critical to make sure that we pick up any defects and fix any defects as soon as we possibly can. So with the wheel and tyre assembly fitted on the aircraft, it may not be possible to inspect the complete wheel, but we should do as much as we possibly can. Obviously, the AMM is going to direct whether we take the wheel off or not. But once the wheel's removed, then we can have a good look over it and make sure everything's tickety-boo. Yeah, so if we've got the wheel on the aircraft, what we're going to look for, cracks, corrosion, distortion, dents, scores, small children, fridge freezers, anything untoward we're going to look for. The tie bolts that tie the two halves of the wheel together, they do shear. Yeah, so the tie bolts and the nuts, the inflation valves, balance weights, all got to would check that they are secure. Yeah. If we find a tie bolt that is defective, the whole wheel should be removed and the complete set replaced in a workshop. That's written on the slide in red. Yeah, and it's also written on page 30. Yeah. Second bullet point, if any tie bolt is found defective, the wheel should be removed and the complete set renewed. Yeah, again, with your highlighter through there. Yeah. Check the wheel, the brake, the tyre, overheating, any signs of overheating, damaged paint, any distortion. And another good sign, if you see grease leaking from the bearings, that's a good sign of overheating. The grease has overheated and started melting, gone from the grease consistency to a liquid. So have a look for grease. That will give you an indication you've got an overheated wheel. Any aircraft, and especially at the moment where we're not getting much flying doing, if the aircraft's in storage or hasn't been moved for a long time, what we need to do is just stick a jack underneath and rotate the wheel for 45 degrees. Give it a good spin just to make sure that the bearing's running smoothly and that there's no flat spotting on the bearing. And likewise, when you lower the aircraft, make sure that it goes down onto a fresh point on the tyre, just to even out the wear that the tyre's taking. Yeah. Big thing there, that note. Yeah. Before we do any work on a tyre assembly, if a wheel comes off, and some places mandate that you deflate a tyre before you remove a wheel from the aircraft, the tyre's got to be completely deflated. We used to, I must admit, we didn't completely deflate it, but we used to let a lot of the pressure out prior to removing the tyre, just for safety's sake. Again, but before a wheel's dismantled, before the tyre assembly is removed from the wheel assembly, we need to make sure that all the pressure has gone. Yeah, it can be fatal if we don't ensure that. So dismantle the wheel, yeah, take off the aircraft, dismantle it down, thorough inspection, clean everything. Yeah, and we might need to use NDT techniques to find damage. That one you can just see the crack running from the bolt hole. Yeah, small crack there. That was an example of the bolts can shear. Yeah, and it might not be obvious. That one, you can tell by the colour of the thing, it had been sheared for a long time. So it might not be obvious, you know, just give the things a rattle. Yeah, so dismantle wheels, thoroughly cleaned, yeah, examined. Some manufacturers require that all the paint should be removed from the wheels before checking for cracks. So if we have to do that, strip the paint off, chemical paint strippers, and make sure you clean all the paint stripper off, because that burns as well, that hurts. A good look round, yeah, you're looking for cracks around bolt holes, certainly at the flanges of the wheel, areas around the flanges, they are particularly prone to cracking. So it might not be obvious either, yeah. So you need to keep your eyes skinned there. Again, NDT can help if it's required. Surface corrosion, yeah, look for that and treat it accordingly. Yeah, so we're cleaning, removing the paint, examine for cracks, NDT, looking around bolt holes in the bead seat, corrosion. If it's really heavy, then the wheel's unserviceable. It can go back off to overhaul. The drive blocks that are used to attach the wheel to the brake unit, just make sure that they're secure and not damaged. They do get battered occasionally. Just look for distortion of the wheel and signs of overheating that we've already mentioned. Your bearings, yeah, plenty of lubrication, not rough running. Yeah, ting 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 ting. Bearings inspected, removed, thoroughly clean, thoroughly inspect. Various conditions that you're looking for, corrosion, brinelling, all that sort of thing. Once they're deemed serviceable, bearings should be repacked with the approved grease and stuck in a poly bag just to protect them from dirt and dust and all the rest of it. With your bearings as well, I can't remember whether it's now or later, but when we're packing the bearing, it should be roughly 2/3 full of grease, of lubricant. Your tie bolts that we mentioned, yeah, you can have a good look at those, make sure that there's no obvious damage. Self-locking nuts, yeah, if it's permitted, they can be reused. Some manufacturers may require that they all be replaced. Wheels painted, reassembled, balanced all in accordance with the manufacturer's instructions. Yeah, and once the tyres assembled on the wheel, obviously the balancing can take place to make sure that we're not going to get any vibration. Right, we're fleeing through this lot quite nicely. So what we'll do there, we'll stop and we'll have a 15-minute break. Yeah, and then we'll go and have a look at tyres and see what we can do with them. So I'm at that 14:25. So we'll see if 14:27. So 14:45 my time. 15 minutes. Yeah. Okay.
Okay, sir.
All right. I'll see you in a few minutes then. Hello. How are you? Right, everyone back, hot to trot. Stretch legs, stretch arms, etc., etc. Next little bit then that we need to look at are aircraft tyres. Yeah, part of the undercarriage system, our tyres. Obviously, we were talking about the undercarriage and the conditions that faces, but the tyre itself has got to withstand a huge range of conditions. Yeah, sitting on the ground, it's going to support the weight of the aircraft on it. Yeah, during taxiing, it's got to be a stable, cushioned ride. That heat that's being generated, the tyre's got to resist that. And it's got to resist the wear and the abrasion that it's going to undertake while it's moving around. During takeoff, the tyres got to be able to take the aircraft load, but also the forces generated at high speed while we're roddling down the runway. Yeah, that tyre's going faster and faster and faster. Heat's generating, but we've got that vibration as well. We've got the forces that the speed's generating. Other way around, yeah. When the aircraft is coming into land, the first point of contact between the aeroplane and the ground is the tyre. So it's going to absorb the impact shocks. Yeah, and then once it's done that, it's got to cope with all the braking loads that the aircraft's going to produce. Yeah. So as well as doing all that, we want it to last a long time as well. Yeah. So these things have got to be very, very strong, very, very robust. Give as long a service as they possibly can. Yeah. So support the weight of the aircraft on the ground. Yeah. During taxi, provide the stable, cushioned ride. Loads during takeoff, yeah, loads during landing, braking loads, and a long life to boot. Yeah, so bless them, they do cope with a lot, our little tyres. Yeah, and again, that's just a good example of some of the damage that can occur, some of the damage that they've got to put up with. Yeah, just for interest's sake, while the picture's there, these little blocks here are the drive blocks for the brake unit, because the wheel is, as we'll see later, is driving the brake around with it. And these little shields here, these little metal plates, are the heat deflectors. So that those deflectors are deflecting heat away from the wheel during braking. Two types of tyre in use for the aircraft. There are tubed tyres and tubeless tyres. Yeah, so depending on the size of the aircraft, type of the aircraft, depends whether we put a tube in the tyre or not. So the two types that we're going to come across, tubed and tubeless. Yeah. The tyre itself is divided into regions. Yeah. So when we talk about the regions of the tyre, we have the crown area, and the crown of the tyre is where the tread is located, manufactured. Yeah. The shoulder of the tyre, yeah, joins the sidewall to the crown. And the shoulder is the area where the reinforcement, the undertread, and the carcass plies are all located. Yeah, so that's where the probably the wrong expression, but that's where we start to beef it up for where it's going to come into contact with the ground. The sidewall is the area where all the carcass plies are located, and that gives the sidewall flexibility. So you can imagine the wheel stuck, it's got the tyre stuck onto it. Yeah, as the tyre hits the ground, it needs to flex, and that flexing takes part in the sidewall. And the bead area is where we put wire bundles, to provide strength to anchor the tyre to the wheel. So that the plies that go to make up the carcass of the wheel are wrapped around the beads, and the beads tend to be metal steel wire bundles or thick bits of steel wire. And as it says in the notes, that's where the tyre's anchored to the wheel. Okay with that? So those are the tyre areas, yeah. Carcass plies are what make up the body of the tyre. Then we get the reinforcing plies as we come up to the top, and on top of there we get the crown, which is the thick rubber bit that's got the tread in it. Yeah, the shoulder is the sort of transition area, if you like. Yeah, so again, just taken from the notes, the tread area, yeah, the wearing surface, yeah, we've got the reinforcing ply and the under tread there. Shoulder area, yeah, where the crown of the tyre starts and the reinforcing starts at the shoulder. Then we've got the sidewall where all the plies are, where all the flexibility of the thing is, and then your bead area where the plies are all anchored about that, and that gives us the strength where we're fitted to the wheel. Construction of the tyres, it's the same for tubed and tubeless tyres. The rubber is natural rubber, and it's reinforced with several layers or plies of nylon fabric impregnated with rubber, and that forms the tread formed the rubber tread and bound with steel wire beading. Yeah. The nylon fabric reinforces the rubber casing, and as the material is impregnated with natural rubber, so the tyre can flex. So as you can see from the slide, we've got the bead, yeah, and what we do is we wrap the plies around the bead, and that's where the anchoring takes place, and then we build up the layers of ply. Yeah. There are two types of ply construction: the radial ply, yeah, and the bias ply. The radial ply, each layer of ply is laid at an angle of 90 degrees to the center line or directional rotation of the tyre, and each successive layer is laid at the same angle. So again, for that, on page 34, that last paragraph, stick your highlighter through there. The radial ply, each ply is laid at 90 degrees to the direction of rotation. Yeah, and built up and built up and built up. So that's all your carcass put together. Yeah. Radial ply tyres, 90 degrees to the direction of rotation, and all of them are laid at that 90 degrees. The bias ply tyre, yeah, again, we're building the bias ply up. The ply is wrapping around the beads, but with the bias ply, each ply is laid at 30 degrees and 60 degrees to the angle of rotation. Then they are alternated until we get to the amount of plies that we need. Yeah, so each ply laid at angles between 30 and 60 degrees to the center line or the direction of rotation of the tyre. Successive plies laid with the chord angles opposite to each other to give a nice balance. Yeah, so that's your bias ply, 30 degrees, 60 degrees. and that is at the top of page 36 and is worthy of your highlighter as well. Yeah. Again, just showing how the tires built up. Yeah, we've got the beads, the wire beads, and around the wire beads wrap our plies. And depending whether it's radial or bias, depends how the plies are laid down, and they're built up and built up and built up. Then we get to what they call the reinforcing plies. Yeah, and the reinforcing plies living just below the outer layer, yeah, the tread layer. Reinforcing ply, yeah. Other bits we've talked about. We'll look at the tread and the grooves in a couple of minutes. So when a tire gets worn, yeah, it'll come down to the tread reinforcing ply, and it's those nylon elements that you see when the tire's worn to limits. Yeah, if we go any deeper than that, we're in deep shit. The other thing with the tire, and again I'll go through it with the notes in a minute just to make sure I've not missed anything, is the inner liner. And it's very, very important that the inner liner is intact, because that's the bit that keeps all the gas within the tyre. Yeah, don't forget it's a tubeless tyre, so that inner liner is impervious. Yeah, it's bonded onto the inside, vulcanized onto the inside, but it's the inner liner that keeps the gas in the tyre. So just the construction features, again reading through the notes to make sure I've not missed anything. The tread refers to the crown area of the tyre in contact with the ground. Grooves are moulded into the tread area, and those grooves allow water to escape from between the tyre and the runway surface, which helps us to grip the runway when we're scooting up and down. The tread formula, the compound that it's made out of, is there to resist wear, abrasion, cutting, cracking. So it's a long life, the tread. The undertread, designed to improve the bonding between the tread reinforcement and the carcass body. Some tyres can be retreaded, so that rubber layer will be of, sufficient thickness to act as the interface for buffing the old tread away and laying the new tread on. Yeah, so it gives us that barrier layer, if you like. The carcass plies, nylon fabric cord sandwiched between layers of rubber. Carcass made from multiple layers of carcass plies, each one adding to the strength and the load-bearing capability of the tyre. Plies are anchored by wrapping around bead wires, forming what they call the ply turn-ups. So it's the bead wires that are the anchor for the plies, and the plies just wrap round. The beads or the bead wires anchor the tyre to the wheel. Yeah, fabricated from steel wires laid together, embedded with rubber. Can be multiple to form a bundle, and then they're wrapped around with a nice rubberized nylon fabric for reinforcement. Chafer strips that talks about just protective nylon fabric or rubber laid over the outer carcass, just again, as the name suggests, just to give it a bit of protection. The liner is a layer of rubber which resists the permeation of nitrogen and moisture through the carcass. The liner, vulcanized to the inside of the tyre, extends from bead to bead, and the liner replaces the inner tube in common with tube tyres. In tubed tyres, a different thinner lining materials used. Yeah, but with the tubeless tyre, we need to keep the gas in, and it's that liner, that inner liner, that allows us to do that. Sidewall, layer of rubber covering the carcass plies to protect them. Tread reinforcing, yeah, just sits underneath the tread. Don't need to worry about that. Breaker plies, don't need to worry about that. Protector plies, again found in retreadable tyres and placed in the crown area, and allows us to, it gives that bit of protection. Yeah, belt plies, don't need to worry about those. Happy days. Tread patterns, yeah, we get different types of tread pattern. The most common, as it says on page, what page are we on? 39. Yeah, we've got the circumferential groove, which is just the groove that goes right the way around the tyre. Yeah, deep grooves cut into the crown and allow water to be dispersed from between the tyre and the runway surface. The plain tread, yeah, is a smooth treadless tyre for use with light aircraft and helicopters that require short takeoff and landing, or they've got vertical landing characteristics. So we don't need to get rid of water from underneath them, so we can just use a plain tread. And the other type is the chined tyre, and that's a chine. It's a rubber shoulder, if you like, embossed onto the side of the tyre. And the purpose of the chine is to deflect water and slush and snow away from the intakes. Yeah, so as the aircraft's rocking down the road, a lot of water, that chine is going to deflect that water away, so it's not going to get swallowed into the intakes. That, again, whatever page we are, page 39, chined tyres. It's worth making a note of what the chines are for. Yeah, you can get single chine and you can get double chine. Again, depends on the aircraft and what you're doing. Hello?
Which one need to highlight earlier? This chime tyre is...
Yeah, what's the purpose of a chine on a tyre?
Okay. Okay, thank you.
Okay. Right, tyre markings then. Yeah, tyres have got different markings on them. And the amount and the type of markings depends pretty much on the manufacturer. But there's certain information that we need to know that's going to be embossed on the tyre. The first thing, the manufacturer's serial number and the date of manufacture. Yeah, we'll have that on. We'll have the part number of the tyre will be embossed onto the tyre, and the dimensions of the tyre. Now, the dimensions, as we'll see, pretty much depends on the manufacturer. Different manufacturers put different dimensions on. But what we need to know the diameter of the tyre. So in this case, we're going to have an outside diameter and an inside diameter embossed. And we need to know the width of the tyre. So that little lot grouped together is going to give us the size code, but it's telling us the outside diameter, the tyre width, and the inside diameter in this case. Tyres that are permitted to be retreaded, we're limited to the amount of retreads we can carry out. So what we do on the tyre, we'll put on a retread indicator, and that'll tell us what number retread the tyre's undergone and when it was carried out. So it's had its first retread in April '89. Yeah, in this case, might have R2 in June '91. Depends how robust the tyre is, how long it's lasted for. But that's an example of the type of marking that we'll come across. The creep indicator Some tyres have these on, other tyres we need to paint the creep indicator on. And that tells us whether the tyre is creeping on the wheel hub. Yeah, if the tyre was creeping on the hub, it's not so much as a problem with a tubeless tyre, but if you've got a tube tyre, if the tyre starts moving around, there's a good possibility it's going to shear the inflation valve. So we need to know that the thing's not moving. With a tubeless tyre, if you get creep, it could break the seal on it's unlikely, but it's possible it could break the seal between the bead and the tyre, and that would cause a leak. So we put these creep indicators on. The problem with the creep indicator, obviously, because the tyre's working in all sorts of crap and rubbish, and the brakes are kicking out lots of dirt and dust, those things get hidden very, very quickly, and they're quite difficult to see. Yeah. Yeah, so we've talked about those bits. The other indications that we come across on the tyre, a little red dot or a little red triangle marked on the tyre. And again, just let me find this. Let's just break down the part number. Yeah, a red triangle, a red spot indicates the light spot of the tyre. Yeah. In tubed tyres, it's used for wheel balancing, whereas we can put the light spot of the tyre against the heavy spot of the tube where the inflation valve is. Yeah, tubeless tyres, the heavy point of the wheel assembly is generally where the inflation valve is. So we line up the red dot or the red triangle, the light spot, we line that up with the inflation valve on the wheel, and that helps to balance the wheel. We also have what they call all vents, yeah, and those are little green or grey painted spots, and they indicate the places where little vents within the tyre are placed during manufacture. What happens when ding ding ding? When they're building the tyre up, all the plies go together. Yeah, and they get glued to one another. But part of that process, yeah, where the plies are joined in, what can happen is we can get little air pockets trapped. It's just part of the manufacturing process where the plies are put together. So what we need to do is to provide some sort of escape path for that air between the plies. So as the tyre's being inflated, yeah, that air is going to get forced out, and it comes out of these little pinprick channels that are marked in green on or grey on the side of the tyre. It allows any trapped air trapped during the manufacturing process to escape, and that's what our all vents are for.
Jim.
Yeah.
This light spot, this red triangle is in line with the inflation bulb?
Yes. Yeah, when we assemble it, we put that red spot, that light spot, in line with the inflation valve to help balance the wheel.
Okay, to balance the wheel.
Yeah.
How does it balance, Jim?
Because you've got a light spot on the tyre, yeah, the inflation valve is a heavy point on the wheel. So it's just light. If you had them on opposite sides, you'd have a heavy spot on the wheel here, and a light spot on the tyre there. So it could set up a bit of vibration. Yeah, so it's just there for, but you know, when you take your car tyre or your car wheel and you get a tyre replaced, and they put little balance weights on, don't they?
Okay.
Yeah, it's the same sort of thing. On our aircraft wheels, we can still have balance weights put on. Yeah, but just part of the balancing process and good practice is to line up the light spot with the inflation valve.
Okay, sir. Thank you.
Okay.
Okay.
Right, the tyre markings, I've covered that, I've covered those bits. The example for the dimensions, yeah, it mentions that. The part number is the only means of identifying a tyre to make sure you've got the right one. Even though a tyre might look the same as another, it could have a different ply rating or whatever. So you can only use part number to identify. Serial number, don't worry about that. The serial number just breaks down and gives us various bits of information. And each serial number is unique to its manufacturer. The ply rating, page 41, the ply rating indicates the strength of the tyre. Originally, it used to relate to the number of plies, but now it's just giving us the strength of the tyre. We might find a speed rating on the tyre, yeah, and that just gives us the maximum operating speed. Whether it's tubed or tubeless, radial or bias, yeah, it'll tell us whether it's a radial ply or a bias ply. We're not allowed to mix tyres. Generally, if you've got a radial on one side, you've got to have a radial on the other side. You can't normally mix them. Manufacturer's trademark, yeah. Again, it says mixing the tyres is not normally permitted. So if you've got Dunlop fitted on one side, you need to have Dunlop fitted on the other side, or Goodyear, or whatever it might be. Again, on page 42, please stick your highlighter through the all vents. Yeah, green or grey spots indicating where the all vents are, and the all vents there to allow air that's trapped during the manufacturing process to escape. And the light spot, the red triangle or the red spot, indicates the light spot of the tyre, and we're going to use that to assist with balancing the wheel tyre assembly. Yeah, it'll line up with the inflation valve. Definitely stick a highlighter through those two, the all vents and the light spot. The retread indicator, we've mentioned that. And again, on page 42, aircraft tyres may be retreaded as many as 10 times during the lifetime. So we can go up to 10 retreads. Yeah, so long as the rest of the tyre is okay, we can replace that crown area up to 10 times. Well, once you've hit that, you kind of got to scrap the tyre then. Creep, tendency of the tyre to move relative to the wheel. More dangerous in tube tyres than it is in tubeless, because the creep, as the tyre moves around, it could shear the inflation valve and cause the tyre to deflate rapidly. Yeah. Not very likely on tubed tyres, but still we can have the creep marks there. Yeah, that red spot we were talking about. Yeah, if you line that up with the inflation valve, if the tyre's moving, if the inflation valve and the light spot are out of line, that's an indication of creep. So you could use the light spot as a creep indicator. Like I said before, the brakes, the creep indicators get covered in crap and they're very difficult to see.
Jim, this light spot is the creep indicator?
You can use it as a creep indicator, yeah.
Okay. Okay.
Hang on. Right, if that's my wheel and I put a tyre on, yeah, and that's my inflation valve on the wheel. Yeah, what I'm going to do is line that inflation valve up with the red spot on the tyre. Yeah, heavy spot, light spot, that's going to help to balance the wheel. You agree with that? Now, if I've got those two lined up, if the tire starts to creep, yeah, if the tire starts to move, if those two are out of line, it means that the tire's moved on the hub. So I've got my creep indication using the light spot.
Okay, thank you.
Yeah, it just saves you painting marks on the tire. You've probably seen it yourself. A lot of aircraft, the creep marks are actually painted on the wheel, painted on the tire. But we can use the light spot. As long as you can see it, we can use the light spot instead. So creep, yeah. Not so critical on tubeless tires, but it is quite iffy on tubed tires. And then it just gives us a few ways of avoiding that. Don't worry about that. Wear indicators, where they're gone? Just give me a second. Yeah.
This is also called balance mark as well, right? Light spot.
It's there for balance, yes. It helps with balance. And the reason we're going to balance the wheel is just to make sure it's not vibrating when it's rotating. Yeah, to make sure that the wheel and the tire are balanced together. It's exactly the same process when you change a car tire. Yeah, you go and change your car tire, and they'll balance the wheel for you. And what they do is they just put little weights on. Yeah. They do that with the aircraft ones as well at times. Little balance weights on. Right, there's a bit on maintenance on page 44. Yeah, it doesn't appear on the slide, I don't think. No. The bit on page 44, yeah? Tyre manufacturers specify an inflation pressure for each tyre, and that inflation pressure applies to a cold tyre with no load on it. So the tyre pressure should be increased by adding an allowance of about 4% when the tyre's got the aircraft weight on it. Yeah. Normally, you're going to get a 5 to 10% tolerance when you're inflating your tyre. The manual will tell you what pressure it should be. Yeah, maybe 350 psi plus 10 minus 5. Maybe 350 psi plus 15 minus nothing. Yeah. So check, but we've got this tolerance to allow for the weight of the aircraft, and when the tires are hot after landing, obviously the pressure is going to increase in the tire, so we can account for that as well. Yeah, right. Comes up on the slide in a minute, but page 44 again, when it talks about inflation procedures, the tyres fitted to braked wheels of aircraft over 5,700 kg MTWA must be inflated with nitrogen. Yeah, so large aircraft, anything over 5,700 kg, got to have nitrogen in the tyres. Yeah, it then goes through to tell us how to blow the tyres up. We're not too fussed. Again, we'll follow the manual. But whenever you're topping a tyre up, you must go through a pressure regulator. Yeah, I've seen it happen where somebody didn't. Tyre exploded, and the guy that did it was very, very lucky to walk away with his life. They really do go with an awful bang if you overpressurize them. So always, always, always go through a pressure regulator when you're inflating tyres. Cold tyres, any tyre that's below 10% below the loaded inflation pressure should be rejected. Between 5 and 10% below the loaded inflation pressure, reinflate and then check them again. Yeah. If pressure goes below 5% again, rejected. Tyre pressure is normally checked before the first flight of the day when they're cool or ambient. Pressure from each tyre checked, noted, compared with the pressures of the other tyres on the same undercarriage leg. Any tyre with a pressure of 10% or more below the maximum recorded, reinflated and rechecked. So all we're doing is just making sure that we're in the right pressure. If we're starting off and it's nice and cold, the party line is if it's 10% below the loaded inflation pressure, it should be rejected. It says rejected with a companion tyre on the same axle. That's because the other one will have taken more than its share of the load. Yeah, examining tyres. Yeah, visual examination prior to each flight. Have a good look over for anything embedded in them, stones, flint, glass, anything like that. Cuts and scores. Yeah, see if there are any. Check that there might be impermissible limits. Bulges indicate that the tyre casing's failing. So if you see bulges on the tyre, again, reject it. And wear. Yeah, for wear on the tyre, we're going to have indicators of some description. Recommended that tyres be removed when wear's reached its limits. Groove tyres with tie marker bars until we go down to the top of the marker bar. Yeah, little marker bars, little rubber blocks in the tread, in the middle of the groove between the treads. We can go down to the top of those bars, and that's us one to limits. Groove tyres without tie marker bars, 2 millimeters is the wear limit. Yeah, so if we haven't got the bars on there, a tread depth of 2 millimeters. Some tyres, yeah, we've got the wear indicating groove. Once we get to the bottom of that centre groove, that's the tyre worn to limits. And likewise, this one, we go down to the bottom of the centre grooves. Yeah, so marker bars, indicator grooves, measurement, yeah, all indicate that the tyre's worn. Once we've reached the wear point, then we reject the tyre and it can go off and get retreaded or whatever. Plain tread tyres used until the casing cords can be seen through the tread rubber. So we take that right down to the cords. And again, that's just a picture we had. Yeah, very, very, very important. Cap 747, you should have highlighted it. But the fact that all braked wheels fitted to aircraft over 5,700 kg must be inflated with nitrogen. Yeah. Cap 747, tyre inflated with air and subject to excessive heat, possibly caused by a dragging brake, can produce volatile gases, may result in a tyre explosion in the landing gear bay and an in-flight fire risk. That was the one I was telling you about the other day, the Nigerian aircraft in Saudi. Hot brakes, they retracted the undercarriage, the heat had nowhere to go, built up pressure, tyre exploded, and that caused a fire, yeah, and the loss of the aircraft. So now, by using nitrogen, we're reducing the risk of that fire because it's an inert gas. Use of nitrogen will reduce wheel corrosion as well, tyre fatigue, and the risk of fire when fusible plugs melt. Yeah, all aircraft, big red letters on the screen there. Make sure you highlight All brake wheels, retractable landing gear fitted over 5,700 kg, must be inflated with nitrogen. Oxygen content must never exceed 5% by volume. If it's not possible to use nitrogen, the air may be used. If air is used, an entry must be made in the tech log. The tyre must be reinflated with nitrogen at the earliest opportunity or within 25 flying hours, whichever is the sooner. Yeah, and all that is down on page 48 in a big box. Yeah, and stick your highlighter through the full Monty of that little lot. Before I go on to tubed tyres, just to finish off the bits after wear, we talked about creep. Other defects we can get sponginess, where the rubber's been affected by fuel or oil or whatever. Flat spots on the tyre. Normally, if the aircraft's been sitting for a long period of time, it can flat spot at the bottom. The way to get rid of that is just to take the aircraft out, tow it around for half an hour, and that should even itself out. Yeah. If we know that the aircraft's going to be sitting for a length of time, every so often, every couple of weeks, just turn the tyres, turn them through 15, 20 degrees, yeah, and do that every couple of weeks. But flat spots, yeah, if we get a flat spot, remedied by towing and taxiing the aircraft for a short distance. Page 47. Deflated tyres, yeah, tyres have been under load while in a deflated condition should be removed from the aircraft. If the aircraft's taxied with a tyre, the deflated tyre and its axle companion should be scrapped. Yeah, so if you've got two wheels on an axle, one of them deflated, then the other wheel should be replaced at the same time. Yeah. More than one of the tyres on a multi-wheel undercarriage found to have run in a deflated condition, then all the tyres on that undercarriage should be. When it says scrapped, they'll go off to the workshop and they'll take the appropriate action. Rejected takeoffs, we've already talked about those. We know about those. Protection, yeah, if the aircraft's parked out for any length of time, need to put wheel covers on just to protect the tyres from any oils, fuels, lubricants, all the rest of it. Anybody got any questions there at all? Anything there? Anybody need a 5-minute break?
Yes, please.
Okay. Well, I'll make that 15:30, so we'll say 15:35. We'll just have 5 minutes and then I'll get finished off. Okay?
Okay.
Okay, should we continue? Get
Hello,
this lot
Jim.
finished off.
Hello, Jim.
Yeah.
In our notes in page 45.
Page 45.
Yes, there is one bracket with the note. There is one note.
Yeah.
On tire with reinforced treats, several layers of nylon fabric are molded into the tree rubber and will become visible during normal use. The threads so exposed should not be confused with the casing. These tires are provided with marker tie bars. Can you please explain what this marker tie bar is?
Yeah, the tie bar is just a rubber block that's in the between the treads.
Okay.
That's my pen. That's the top of the tire. You get the grooves in the tire, yeah. You see on the screen?
Yes,
can you see the screen?
yes,
yeah. In the bottom of the grooves, yeah, you get like a little block of rubber, yeah, and when you that's your marker bar, your marker tie bar, and when you hit the top of that, when the tire's worn down to level with the top of the marker bar, that's the tire worn to limits. So then we need to replace it.
Okay, Jim. Thank you.
Yeah. Anybody else? Right, fitting tyres then, fitting tubed tyres. Again, there's going to be a procedure. I'm just going to whip right through it very, very quickly. Yeah, ensure that the tyre's clean, FOD-free, nothing's stuck inside it. Dust the thing with the tube with French chalk. Smooth out the tube, partially inflate it, and then pop it onto the wheel. Yeah. Pop the tyre around, yeah, and when you're putting the two together, just make sure that the tube isn't nipped. Yeah, so you're not catching the tube. When it says not nipped, you're just not catching the tube to puncture it. Inflate the tube so that the bead's seated. Inflate the tyre so that the bead's seated, and then tighten the tie bolts up and torque load them. Yeah, tubeless tyres are even easier. Yeah, before you fit them, have a good look round. Check the wheel, make sure that there's no damage on the wheel. Lubricate the seals with the appropriate compound. Check that your balance marks are there, ready to align those up. Assemble the wheel and then inflate it. Once we've inflated, we need to pressure test. And part of the pressure test is allow the wheel to vent. What page is this on? Because this is worth noting. Yeah, so fitting tube tyres to wheels, easy enough. Don't worry about any of that lot. Split wheels. Before the tyre can be fitted, the wheel should be dismantled. Tube placed in the tyre and inflated till it adopts its correct contour. And then put the two halves of the wheel together. Fitting tubeless tyres prior to fitting and do all your examinations. Any lubricants for your seals, make sure that's applied. Tyre positioned on the wheel, balance marks aligned. Yeah, split wheels. Bolt threads should be lightly lubricated, it says, with a grease. Again, don't worry too much about that. But inflation after tyre fitting. Yeah, after fitting tubed and tubeless tyres should be inflated in a test to a test pressure specified. Nitrogen should be used. Screw on type of connector. Go through a regulator, as we said before. And if you're inflating a tyre, it should be done in a safety cage. That safety cage is there because if anything does go wrong, if it does blow, the safety cage will contain the explosion and reduce the chances of harm to you. All tyres inflated slowly. Important with tube tyres. Yeah, inflate slowly and then take them up to the required position. Testing of tubed or tubeless tyres normally by means of a duration pressure test, but if you haven't got time, you can dip them in water and look for bubbles. Yeah. On all tyres, you're going to get a pressure loss in the first 12 hours because of tyre stretch, and also because of that venting that we were talking about. With a tubeless tyre, venting from the awl occurs in 3 stages. The first stage, very, very rapid, ceases after about 20 minutes. Second stage, slow seepage over several hours. And the third stage lasts over the life of the tyre. And all it is where the plies are squeezing together. So as the tyre inflates, the plies are being squeezed together, and that's forcing air out initially. As you leave it under pressure, yeah, the rest of that trapped air, or some more of that trapped air, is eventually going to work its way out via the awl holes. And then the third stage is the rest of it coming out, and over a period of time, the nitrogen will leak through that inner lining that we talked about. Yeah, it will get through. It's not 100%, but that's why we check the pressures most days. Yeah, so after testing of tubeless tyres, we've got to wait until the first stage of venting has finished. Otherwise, you're going to get completely false indications. Yeah, so just make a note of that. And on page 51, just the venting, the fact that the first stage rapid, second stage slow, few hours, third stage lasts for the life of the wheel, and testing of the tubeless tyres must be carried out after first stage of venting ceased. Carrying out the pressure test, yeah, check the tyre pressure, record it, leave it for 12 hours, check it. If it's dropped 10%, reject the assembly. If the pressure loss is less than 10%, re-inflate, give it a further 12 hours, and then check the pressure again. Again, that bit on page, whatever that's on, 52, again, just that process is worth noting as well. Yeah, so if you've lost pressure over 10% in the first 12 hours, what should you do with the tyre where it should be, or the assembly, it should be rejected? If the pressure loss is less than 10%, what should you do? Re-inflate and recheck, reject the tyre, or have a cup of tea and cry. Yeah, re-inflate and recheck. Watch for that one. That one has cropped up before now. Yeah. Bit about removing tyres. Yeah. Whatever you do, if you're working on a wheel, if you're working on a tyre, make sure it's deflated. Yeah. Got to be deflated before you try to do anything. And that's the bit to take away from that little lot. How to remove tubeless tyres. I don't think there's anything around there. Just make sure that it's deflated. Nothing there to worry about. No, can't see anything there. Which leads us on to inner tubes. Yeah, inner tubes, there are 3 types of inner tube that you might come across. There's the standard, the thickened, and the cord reinforced inner tubes. Standard tube used on light aircraft, where excessive heat may be generated. Thickened cord or thickened or cord reinforced tube may be specified. So the other 2 are just giving that little bit extra protection. We're not going to worry about that. Inspection of the tubes, yeah, just good look over, look for obvious damage, cracking, perishing, valve stems especially for any damage there. Inflation valves, yeah, the only thing I'd say about the inflation valves, little shredders, always make sure that the valve cap's fitted. It keeps shit out, and if the valve's leaking, it'll keep pressure in to some extent. So your valve cap, make sure that's fitted. The two types of or the valve core, I should say, the Schrader valve type thing. Some wheels you get an extension piece, so you can check tire pressures if they're in an awkward place. Tire pressure gauges, use the right one and make sure that they are in calibration. The little stick ones, they're all right on smaller aircraft. They're not particularly accurate, so you've got to make allowance for that. That's why they need to be calibrated. Your proper pressure gauges, reinforced, because they get thrown about everywhere. The adapters for getting on the tires, and the little handle for inflating as well. These are the ones that we use at the hangar. You just screw that onto your inflation adapter. The needle will read the pressure that's in the tire. Once you've disconnected it, just press the little button and that will dump the pressure out. However, can't reiterate enough the fact that it's PME, so it should be calibrated, and records of that calibration should be checked, so it goes away at the right point in time. Removing and refitting wheels, it just goes through a procedure for that. You can have a read through that for your own excitement, but we don't need to worry about anything there. Just the fact that if you're deflating a tire, deflate it slowly so that the valve doesn't start icing up. Make sure you've installed thread protectors on the axle when you've taken the axle nut off. Nothing there. Follow the AMM, follow the procedures. Lubricate the axle before you fit the wheel. Make sure the bearings are greased. Putting the wheel back on, lubrication. Slide the wheel into position. Protectors that you've fitted, make sure that they're taken off. Torque the nut up and torque it as you rotate in the wheel. And then slacken the nut and then again rotating the wheel, tighten up to the specified torque and lock whatever the method of locking is for that particular wheel, and check your tire pressures once you've finished. Storage of tires and wheels, darkened room away from sources of heat. Tires should be stored vertically and should be supported third of the way up. That might well be module 7 actually, but they've got to be stored vertically and supported suitably. If you're storing tubes, they should be stored in their original wrapping. If you can't do that, then slightly inflate them and put them inside a tire of the appropriate size just to protect them. Assembled wheels not required for immediate use should be inflated to a pressure of 20 to 30 psi for storage and shipment, and then we should have records for them. And ching ching ching. Records, number of landings each tire's made. Should have its own little log card then, basically. Provided the storage conditions are maintained, they'll last for, well, it says about 4 years in storage. After 7 years in storage, tires should be returned to the manufacturer for assessment. So off page 60 there, the only bits that are ringing a bell, the sort of transit pressure, storage and shipment pressure in a tyre, 20 to 30 psi. Yeah, the shelf life, yeah, tyres and tubes may be kept in storage for up to 7 years from the date of manufacturer. And yeah, that was it. Yeah, and stock rotation means that it's unlikely to last more than 4 years. But the two things on there, 20 to 30 psi storage and shipment, and may be kept for up to 7 years from the date of manufacture. Okay with that?
All okay.
Sound right. That was tyres. Then the last little bit on tyres that we'll finish off is aquaplaning. Yeah, aquaplaning is caused by a film of water under the tyre which builds up and it forms a wedge under the tyre and will lift the tyre off the runway. Yeah, so now the wheel's spinning, but it's not in contact with anything. So aquaplaning is really, really dangerous. Yeah. Reduces braking efficiency, reduces directional control of the aircraft. Obviously, if you're not in contact with the ground, you can't do anything. I don't know if any of you guys have aquaplaned in a car, and that's scary enough, but doing it in an aeroplane would frighten the life out of you. So aquaplaning, what we can do to avoid, we need to make sure that the aircraft weight is on the ground as soon as we can. Need to make sure that the tyres are in good condition so we can get rid of the water from underneath when we, again, doing what we can to reduce the chances of aquaplaning. There are 3 types of aquaplaning. There's dynamic, yeah, where standing water forms a wedge and lifts the tyre clear of the runway surface. So basically what's happening with this one, where's my little thing? Yeah, if that's the tyre, the wheel, yeah, runway surface with water on it, and the water can't clear. The water's standing, and it forms a sort of wedge in front of the tyre, and the tyre gets lifted clear of the runway surface. So now that tyre is just rotating and not going anywhere. Viscous aquaplaning, yeah, we've got the wheel, yeah, and the wheel hits a really thin layer of water, but the weight of the aircraft can't break through the water, so that the tyre's rolling on top of the water, and so it's like skating on ice. Yeah, it can't go anywhere. And then your reverted rubber. Reverted rubber is where the tyre has had a bit of a skid, and where the tyre skids, all the rubber starts to block the tread. Yeah. So what happens in effect is that the tread's blocked. The water that's trapped under the tyre can't go anywhere, and it heats up and it creates steam. And that steam builds up such a pressure, it lifts the aircraft off the runway. Yeah. So the reverted rubber is where the tread's all blocked, water can't escape. The viscous is a very, very thin film of water on top of the runway, like skating on ice. And the dynamic is where the water forms a wedge in front of the tyre and just lifts the tyre off the runway. Each one as bad as the other, yeah, but your viscous can occur at fairly low speed as well, which doesn't help matters. Yeah, so the 3 types of aquaplaning, yeah, just how it happens. Yeah, the bit on page, whatever page we're on, yeah, 61. The minimum aquaplaning speed, ground speed, is 8.6 times the square root of the tire pressure in PSI. Yeah. That is the minimum aquaplaning ground speed. Yeah, so the more worn the tire, the greater the possibility of aquaplaning, deeper the tread, deeper the depth of water before it can take place. Good runway surface, crosswinds can cause aquaplaning. Yeah, so if we get to the point where we're around 8.6 times the square root of the tire pressure in PSI, that is the minimum aquaplaning ground speed. Yeah. The example it gives, typical twin engined aircraft, tire pressure is 55 and nose at 50. And that, if you go through the formula, gives the aquaplaning speed of 63 to 61 knots. Yeah, so it's not a huge amount. Typical large transport aircraft, main wheel pressure of 190 psi will have a minimum aquaplaning speed of 118 knots. Yeah, so the calculated speeds for the start of aquaplaning, once it's started, it can continue for as long as it wants, really, because once you're spinning on top of that water, there's nowhere to go. So what they do within the manual, the operations manual, I think it is, there's a figure for aquaplaning, but you guys need to remember that 8.6 times the square root of the tire pressure in pounds per square inch. Yeah, we can reduce the possibility of aquaplaning by ensuring that the weight of the aircraft is put onto the undercarriage as soon as possible after landing. Yeah, so large aircraft, yeah, we're going to use spoilers, and that's, as we discussed yesterday, deploying the spoilers is going to dump all the lift on the wings, put the weight of the aircraft onto the ground, and again, we've got all the flaps in the down position. We're destroying all the lift. We're getting the weight of the aircraft onto the ground as soon as we possibly can after landing. And that, guys, is miraculously smack bang on time for today, and we're right where we need to be. Has anybody got any questions on anything that we've covered this afternoon on landing gear? If you do, have a look through. If you have got anything, give me a shout in the morning, and we can have a look at it. It's all fairly straightforward stuff that we've covered. There shouldn't be anything too complex, and everything that I recognise, I've let you know. So you should be all right that way. So does anybody have any problems, any questions, queries, bribes? No, definitely silence. Well, in that case, guys, we'll call it a day there, and I will see you at the same time in the morning. Enjoy the rest of your evening.
See you.
Okay, cheers then.